The James Webb Space Telescope has quietly revealed something astonishing. Chemistry so unusual it challenges everything we thought we knew about comets. A lot has changed since the discovery of 3I Atlas. The comet has brightened, its tail has stretched across the void, and continues to produce more questions than answers. But what does this frozen traveller mean for us? Could its strange composition tell us about other star systems? Might its path hint at forces we still don't fully understand? And why now are these interstellar visitors suddenly appearing within our watchful gaze? Tonight, we'll explore not only what makes 3I Atlas so strange, but also what it teaches us about the galaxy itself. If you enjoy cosmic mysteries told in a way that helps you unwind, please consider liking this video, subscribing, and sharing your thoughts in the comments below. It truly helps. For now, let your imagination drift. Join me as we journey together into the quiet depths of the universe, where 3I Atlas awaits. For once we found it early. Atlas is inbound, still warming, still observable, giving scientists time to prepare. That detail changes everything. With Oumuamua, discovery came too late. By the time astronomers realized it was interstellar, it was already speeding away, growing dimmer with each passing night. Borisov gave us a little more time, but still slipped quickly through, its secrets revealed only in fragments. Atlas, however, offers something rare: foresight. It was spotted before it reached its closest point to the Sun, while still on its inbound leg. That advance notice opens a door, a window of opportunity to watch its evolution from cold and dormant to bright and active. Astronomers are seizing the moment. Observatories across the world have coordinated schedules, ensuring telescopes are aimed at Atlas whenever possible. Time on facilities like Gemini South, the Very Large Telescope, and of course, the James Webb Space Telescope has been set aside. Each one collects different kinds of data: images to capture its changing appearance, spectra to decode its chemistry, polarimetry to study its dust. Piece by piece, the comet's story is unfolding. This coordination matters because Atlas will not stay bright forever. By late October 2025, it will reach perihelion, its closest point to the Sun. The glare will make observations difficult, if not impossible. Only weeks later, it will slip outbound, cooling and dimming, eventually fading beyond reach. The months between discovery and departure are all we have, a cosmic clock ticking steadily toward silence. For scientists, this fleeting opportunity is priceless. Imagine being handed a sample from another star system, but only for a few months, and only if you study it from afar. Every observation counts. Every photon of light that enters a telescope carries a message about where Atlas came from and what it is made of. And so, around the globe, astronomers work long nights, calibrating instruments, refining predictions, planning for moments when the comet will be clearest. They know they cannot stop its departure, but they can capture its essence before it vanishes. That is the beauty of this moment. A fragile window, brief yet profound, offering humanity a chance to learn from a traveller that will never return. For billions of years, these objects passed unnoticed. Only now, with modern surveys and machines that never sleep, do we catch them drifting by. It is easy to imagine that Atlas, Oumuamua, and Borisov represent something new, that the universe has only recently begun to send us these wandering fragments. But the truth is far simpler and more humbling. These travellers have always been here. They have slipped silently through our solar system countless times in the deep past. We just weren't watching carefully enough to notice. The cosmos is vast, and interstellar visitors are small. They do not blaze across the sky like the comets of old paintings, stretching tails from horizon to horizon. Most appear only as faint points of light, lost in the background unless a telescope happens to look in exactly the right direction at exactly the right time. Until recently, the odds of catching such a thing were close to zero. For centuries, astronomers relied on human eyes pressed to glass, charting the heavens by hand, noting movement over nights or weeks. Against the immensity of the sky, the chances of recognizing an interstellar object were vanishingly small. What changed was technology. In the last few decades, wide-field surveys transformed our watchfulness. Telescopes like Pan-STARRS in Hawaii, Atlas in Chile, and soon the Vera C. Rubin Observatory in the Andes scan the skies with relentless rhythm. Night after night, they photograph the entire dome above, storing terabytes of data. Software, not human eyes, combs through the images, searching for anything that shifts or brightens, anything that refuses to match the catalogue of known stars and asteroids. What once took lifetimes of patient recording now happens automatically, continuously, and without fatigue. This new vigilance explains why interstellar objects suddenly seem common. First, Oumuamua, then Borisov, now Atlas. 3 in less than a decade after none in recorded history. Not because the galaxy has changed, but because we finally opened our eyes wide enough to see. What seemed impossibly rare is revealed to be part of the background fabric of our skies. Astronomers now suspect that interstellar debris may be abundant, a steady rain of fragments tossed out of planetary systems across the galaxy. Each star births its own planets, and in the process, many icy bodies are flung outward, never to return. Over billions of years, these wanderers drift through interstellar space, cold and dark, until some happen to brush near our sun. The difference now is that we can catch them, catalogue them, and study them before they vanish again. Think of what this means for the future. With Rubin Observatory's 10-year legacy survey of space and time about to begin, the expectation is that more interstellar objects will be found not one per decade, but many, perhaps dozens. Each will carry a new sample of alien chemistry, a fresh clue about the diversity of worlds beyond our own. Some will look familiar, like Borisov. Others will puzzle us, like Oumuamua. And some, like Atlas, may exist in the in-between, blending traits we know with mysteries we do not. There is something poetic about this shift. For most of human history, the night sky appeared changeless. The stars held their positions, the constellations returned each season, and only the rare comet or nova disturbed the illusion of permanence. Now we know the truth. The sky is alive with motion. Tiny visitors are always passing by, just beyond the edge of our awareness. With our new eyes, silicon, glass, and algorithms, we are finally beginning to notice them. So when we ask, why so many now? The answer is not that the universe has grown busier, but that we have grown wiser. Our instruments keep vigil where once we slept, and in their tireless watch we glimpse what was always there. A steady parade of travellers from other suns, slipping through the silence, reminding us that the galaxy is not still but endlessly in motion. At first it was faint. Now, Atlas stretches a shimmering tail into the dark, alive with activity as sunlight heats its surface. Comets are often called dirty snowballs, fragile mixtures of rock, dust, and frozen gases. For much of their journey through the depths of space, they remain inert, locked in silence, their volatile materials frozen solid. But as they approach the warmth of a star, something remarkable begins to happen. The ices within start to sublimate, turning directly from solid to gas. This process releases jets of vapor, carrying dust grains with them. The once invisible nucleus becomes enveloped in a glowing coma, and from that coma extends the comet's most iconic feature, its tail. For Atlas, this transformation was subtle at first. In its early images, it was little more than a smudge, a hint of haze surrounding a tiny point of light. But week by week, as it drew closer to the sun, the changes became dramatic. Ground-based telescopes, like Gemini South in Chile, began to reveal a stretched veil trailing behind it. Astronomers reported a lengthening tail, brighter and sharper with each new observation. The once quiet interstellar traveller was waking up. What makes the tail so fascinating is that it is not a single structure, but two distinct ones. There is the dust tail composed of tiny particles pushed gently outward by the pressure of sunlight. This tail curves, following the comet's trajectory, forming an arc through the void. And then there is the ion tail, made of charged particles stripped from gas molecules by the solar wind. This tail always points directly away from the sun, a thin, straight beam shaped not by gravity, but by the invisible flow of charged particles streaming from our star. Together, these twin tails paint a portrait of the comet's interaction with its new environment. For Atlas, the behavior of the tail adds to the mystery. Its brightness and activity levels have been stronger than some expected for a nucleus estimated to be only 1 or 2 kilometers across. In addition, hints of green in the coma, likely caused by diatomic carbon or cyanogen, suggest unusual chemistry already active at great distances from the Sun. Most comets do not display such richness until they are far closer. Atlas, however, seems impatient, shedding its material early and abundantly. The tail is not just beautiful, it is diagnostic. By studying its shape, astronomers learn about the forces acting on the comet. By analyzing its spectrum, they uncover what molecules are streaming into space. Every flicker of brightness, every asymmetric feature, tells a story about the nucleus hidden at the core. The sunlit side is far more active, implying pockets of volatile, rich ice embedded unevenly across its surface. Perhaps the comet is fractured, its crust pitted with vents, or perhaps it carries layers of exotic ices never before seen so close to home. To us, the tail is also symbolic. It is the comet's calling card, the luminous sign that an alien visitor has arrived. Long ago, such apparitions filled people with fear or awe, omens written across the night sky. Today, we understand the physics, yet the beauty remains undiminished. To watch Atlas growing its tail is to witness a process that connects us to deep time, to the birth of solar systems, and to the endless exchange of matter across the galaxy. And in the case of Atlas, the growing tail is more than spectacle, it is a signal. A reminder that this comet is alive, dynamic, and alien. Each stream of dust and gas carries the story of another star system, briefly illuminated before drifting once more into the dark. Observers whisper of a soft emerald shimmer around the comet's coma. If true, it may hint at exotic chemistry rarely seen so far from the Sun. Comets have always been associated with mystery, and their colours often spark the most intrigue. To the naked eye, most appear as faint white smudges against the backdrop of the stars. Yet, through the gaze of sensitive instruments, subtle hues emerge, pale blues, ghostly whites, and occasionally an otherworldly green. For Atlas, the suggestion of a green glow so early in its journey raised eyebrows across the astronomical community. The source of such a glow is often diatomic carbon, a simple molecule of 2 carbon atoms bonded together. When exposed to sunlight in the vacuum of space, these molecules absorb energy and re-emit it in the green portion of the spectrum, creating a soft, luminous aura. Another candidate is cyanogen, a carbon-nitrogen compound that can fluoresce under solar radiation. On Earth, both are hazardous chemicals. In the heavens, they are the artists painting comets with emerald light. What makes Atlas unusual is timing. Most comets do not display strong green coloration until they are much closer to the Sun, when the heat is sufficient to liberate volatile molecules in significant amounts. Yet reports suggest Atlas began to show hints of this glow while still far out, beyond the orbit of Mars. That implies either a nucleus unusually rich in these compounds, or one whose structure allows them to escape earlier than expected. Either explanation suggests that Atlas is not just a comet, but an alien comet carrying a chemical recipe different from the ones we know. For astronomers, colour is more than beauty, it is evidence. By breaking down the light from Atlas's coma into spectra, scientists can identify the exact fingerprints of the molecules within. Already, the James Webb Space Telescope has confirmed an excess of carbon dioxide relative to water, an inversion of the ratios found in most local comets. If green glow molecules like diatomic carbon or cyanogen prove abundant as well, it would further set Atlas apart, making it a truly exotic messenger from another stellar nursery. The green glow also carries symbolic weight. Throughout history, such a sight would have seemed uncanny, even supernatural. Ancient skywatchers might have seen it as a celestial serpent or a divine omen, a streak of fire tinged with emerald drifting across the heavens. Even today, knowing the chemistry does not strip the awe, to look through a telescope and see a soft green haze shimmering around a comet's head is to feel the universe reminding us of its strangeness, its refusal to fit neatly into our expectations. Yet the glow is fleeting. Unlike a painted canvas, a comet's colours shift with time. As Atlas draws closer to the Sun, water vapour may become the dominant driver of activity, diluting the abundance of exotic molecules. The early hints of emerald light may be a temporary gift, a reminder of the comet's alien chemistry before the familiar signatures of water take over. For now, astronomers remain cautious, calling for more observations to confirm what early reports suggest. A comet from another star system, glowing green against the black canvas of space, such an image captures imagination as much as it challenges science. And if the glow is real, it tells us something profound. That not all planetary systems are alike. Some produce comets rich in water, others rich in carbon monoxide or methane, and some, like the one that birthed Atlas, may gift us travelers that shine with the soft emerald of alien chemistry. When Webb's instruments locked onto the comet, the data they returned surprised even seasoned experts. A new chemical story was unfolding. The James Webb Space Telescope was built to peer into the earliest moments of the universe, to glimpse the faint glow of galaxies born billions of years ago. Yet its power also lies closer to home. Webb is not only a window into the distant past, but also a magnifying glass for the fragile wanderers drifting through our cosmic neighbourhood. When Atlas appeared on astronomers' radar, it was only a matter of time before Webb turned its golden mirrors toward it. On August 6, 2025, Webb's near-infrared spectrograph, known as NIRSPEC, began its watch. Unlike a traditional camera, NIRSPEC does not simply capture an image. Instead, it splits light into its component wavelengths, much like a prism spilling white light into a rainbow. Each molecule, whether water vapour, carbon dioxide, or methane, leaves a unique signature in that rainbow. By reading these fingerprints, astronomers can determine exactly what a comet is made of without ever leaving Earth's orbit. The expectation was straightforward. Based on centuries of studying comets within our own solar system, scientists predicted that water vapour would dominate. After all, water ice is the primary building block of most comets. Alongside it, smaller amounts of carbon monoxide, carbon dioxide, and other volatile compounds were expected to appear. Webb's instruments, it was thought, would simply confirm this familiar recipe. But Atlas had other plans. The spectra that came back were unlike anything recorded from a comet before. Instead of water leading the mix, carbon dioxide overwhelmed it. The ratio was astonishing: 8 parts carbon dioxide for every 1 part water. Such a reversal defied all expectations. Comets from our system typically release far more water than carbon dioxide. For Atlas, the balance was inverted, as if its very chemistry was upside down. The implications were profound. Perhaps Atlas was born in an environment colder than the outer reaches of our solar system, where carbon dioxide could freeze in abundance while water remained trapped, buried too deeply to escape. Or perhaps its surface layers are sealed in such a way that water cannot yet escape, while carbon dioxide vents freely. Either way, its chemistry is a message. This comet was forged under conditions alien to us, in a nursery shaped by a different star. Yet carbon dioxide was not the only surprise. Webb detected carbon monoxide, a sulfur-bearing molecule called OCS, and plenty of dust and ice grains. The signature was complex, layered, hinting at processes we are only beginning to understand. To astronomers, it was like opening a book written in a foreign language, some words familiar, others entirely new. Beyond the scientific data, there was also an emotional impact. To see an object from another star system reveal its composition with such clarity was breathtaking. For the first time, we were reading the chemical history of an alien comet, not through speculation, but through direct measurement. It was as if a traveller from afar had paused, lifted its veil, and allowed us to glimpse the world it once called home. In the weeks that followed, teams across the world pored over the data, searching for meaning in the unexpected ratios. Papers were drafted, conferences convened, debates sparked. Was this the beginning of a new class of comet? Could other interstellar visitors show similar chemistry? Or was Atlas a true outlier, a rare jewel among the countless icy bodies drifting unseen between the stars. One thing was certain: Webb's gaze had transformed Atlas from a faint blur into a profound discovery. Its golden mirrors, designed to reveal the first light of the cosmos, had also captured something deeply immediate, a messenger from another world, whispering its secrets across the gulf of space. Instead of water vapor leading the mix, Webb saw carbon dioxide 8 times more abundant than water, a comet like no other. For centuries, comets within our solar system have followed a familiar script. At their heart lies a nucleus of ice and dust, and as they approach the sun, water vapor is almost always the star of the show. Sublimating water drives the coma, fuels the outgassing, and shapes the comet's activity. Other volatiles, carbon monoxide, carbon dioxide, methane, appear too, but always in smaller supporting roles. That is why Webb's reading of Atlas came as such a shock. In Atlas, the chemistry is inverted. Carbon dioxide, normally a minor player, takes center stage, outshining water vapor by an extraordinary margin of 8-1. To put this in perspective, most solar system comets have ratios that tilt heavily toward water. The sublimation of water ice is what gives them their characteristic brightness and long tails as they near the sun. Atlas, however, is something different, a comet where carbon dioxide seems to rule. This finding raises more questions than answers. Why would a comet form with such an unusual composition? One possibility is its birthplace. If Atlas formed farther from its parent star than most of our comets did, it may have resided in a region so cold that carbon dioxide froze abundantly while water ice remained locked away, or perhaps never condensed at all. In that scenario, Atlas would carry within it a frozen record of temperatures and conditions beyond anything our solar system experienced. Another possibility lies not in its origin, but in its structure. Perhaps the outer layers of Atlas are rich in carbon dioxide, while deeper reserves of water remain sealed beneath a crust. In that case, what Webb is seeing now may only be the beginning. As Atlas draws closer to the sun, the added heat could penetrate deeper, cracking the crust and unleashing hidden stores of water ice. If so, the comet's chemistry may change dramatically in the months ahead, shifting from carbon dioxide dominance to something more familiar. Yet there is another, more intriguing possibility, that Atlas is not merely unusual, but part of a broader pattern we have not yet recognized. With only 3 interstellar comets studied so far, our sample size is vanishingly small. If Atlas represents a category of comets common in other star systems, it would mean the diversity of planetary nurseries across the galaxy is far greater than we imagined. Some may produce comets rich in water, others in carbon monoxide, others in exotic volatiles rarely found here. Each interstellar visitor becomes a test case in a vast experiment we did not know we were running. For astronomers, this is both exhilarating and daunting. Every measurement of Atlas carries enormous weight, because it may redefine what we consider normal for comets. Already, theories of planetary system formation are being revisited. If carbon dioxide-rich comets are common beyond our sun, then models of how ices condense, migrate, and accumulate around young stars may need rewriting. But beyond the science, there is something poetic in this discovery. Imagine a comet born under a distant sun, its chemistry sculpted in the cold outskirts of an alien system. For millions of years, it drifts in darkness, until chance brings it here, into our instruments, our debates, our dreams. Its unusual makeup is not just data, it is a story, carried silently across the void. Carbon dioxide dominance is more than a quirk. It is a revelation, reminding us that our solar system is not the rulebook for the cosmos. Atlas shows us that the galaxy is richer, stranger, and more diverse than our assumptions allow. And as its icy gases escape into the sunlight, they carry with them a message across the stars. The universe is not uniform, but endlessly surprising. Perhaps Atlas was born in a star system colder than ours, where carbon dioxide piled up while water ice remained hidden away. Every comet is a time capsule, preserving the conditions of the nursery in which it formed. For comets of our own solar system, that nursery was the protoplanetary disk around the newborn sun, a vast, swirling cloud of gas and dust, where temperature and distance determined what could freeze and what remained vapor. Close in, only metals and rock condensed. Farther out, water ice became abundant. Beyond that, colder still, carbon monoxide and carbon dioxide froze, coating small bodies in exotic ices. If Atlas is dominated by carbon dioxide, then it may have been born in the farthest reaches of its parent star's disk, a realm even colder than our Kuiper belt. In that distant nursery, water ice might have been scarce or buried deep, while carbon dioxide, with its lower freezing point, accumulated in abundance. Imagine a world so frigid that what is rare here becomes the foundation of icy bodies. Atlas, cast free from that realm, would then carry its strange chemistry as a signature of its birthplace. Such an origin story reshapes how we view planetary systems. We often assume that what happened here, the way our sun's planets and comets formed, is typical, but Atlas suggests otherwise. Around other stars the rules may be different. Disks may stretch farther, or remain colder for longer. Every interstellar object is therefore a piece of comparative science, allowing us to glimpse the diversity of planetary nurseries without ever leaving home. Consider the scale of this thought. We cannot yet send probes to other star systems. The distances are too immense, the journeys too long, but nature delivers pieces of those systems to us. Atlas is not just a comet, it is a frozen emissary from another sun, carrying clues about conditions light years away. By studying it, we are indirectly studying the architecture of alien solar systems, learning how they build, what they keep, and what they cast out. And Atlas's message is clear. Not all nurseries are alike. Some may produce Oumuamua-like fragments, rocky and barren. Others may produce Borisov-like comets, similar to our own. And some, like the nursery that birthed Atlas, may give rise to carbon dioxide-rich wanderers, their surfaces shimmering with exotic chemistry. Each one tells us that the galaxy is not monotonous but richly varied, a patchwork of environments sculpting worlds in different ways. There is also a humbling perspective in this. Our solar system feels central to us because it is home, yet in truth, it is just one of countless systems, one recipe among billions. Atlas reminds us that what we call normal is only local. Out there, in the cold darkness between stars, countless variations exist, each carrying their own frozen fingerprints. As Atlas passes through our sky, it is easy to think of it as a stranger. But in another sense, it is a gift, a visitor that allows us to reach across interstellar space without ever moving. In its chemistry lies the echo of a place we will never see directly. A frozen nursery under a distant sun, and though Atlas will vanish, the knowledge it leaves behind will remain, expanding our sense of what is possible in the galaxy we call home. Not only the gases, but even the dust grains scattered light in ways unseen before. The comet's particles seemed alien in texture and composition. When we think of comets, we often imagine them as icy bodies, their tails driven by sublimating gases. Yet dust is just as important. Those tiny grains, lifted from the surface by escaping vapors, form the luminous veils we see stretching across the sky. Dust carries within it the mineral fingerprints of the comet's past, fragments of rock and carbon that predate planets themselves. Studying dust is like shaking hands with the building blocks of a solar system. In the case of Atlas, that handshake felt strangely unfamiliar. Astronomers used a technique called polarimetry, which studies how light changes when it bounces off small particles. Normally, cometary dust follows predictable patterns. The polarization shifts in ways that reveal whether grains are small or large, smooth or jagged, bright or dark. But Atlas refused to follow the script. Its light showed an extreme negative polarization branch, deeper than anything measured before. In simpler terms, the dust bent and reflected light in ways that defied expectations. Why does this matter? Because light does not lie. The way dust interacts with photons reveals its size, shape, and composition. For Atlas to behave so differently suggests that its grains are unusual, perhaps clumped together in strange aggregates, or coated in exotic carbon-rich compounds rarely found in our own comets. Some astronomers even speculate that the grains may be darker than normal, absorbing more light than they reflect, or porous, like delicate cosmic foams sculpted in alien conditions. Such findings stretch the imagination. If comets from another system can carry dust so different, then the processes that built their planets and minor bodies must also differ. Dust grains are the seeds from which worlds grow. Their chemistry, their stickiness, their ability to clump together all determine whether a solar system produces rocky planets, gas giants, or icy debris belts. By reading the dust of Atlas, we are glimpsing the earliest moments of another star's history. The surprise also carries a warning. We have studied hundreds of comets within our own system, and from them, we've drawn assumptions about what comets should be, about what they should look like, about how they should behave. Atlas breaks those assumptions. It reminds us that our sample is biased. The Milky Way contains countless other nurseries, and their dust may follow rules unfamiliar to us. For scientists, this is exhilarating. The more unusual the data, the more it forces us to think. Every unexpected polarization measurement pushes theory forward, demanding new models, new simulations, new perspectives. It challenges us to accept that normal is only what we have seen so far, not a universal law. And for the rest of us, there is wonder in the image itself. Imagine particles of dust, smaller than a grain of sand, traveling across interstellar space for eons. They drift, unseen and untouched, until at last they fall into sunlight near our star, scattering light in alien ways. Through telescopes, we do not see the grains directly. We see their effect, the subtle change in light. Yet from that faint signal, we recognize their strangeness. In its dust, as much as in its gases, Atlas speaks of its origins. It is not simply another comet with a familiar recipe. It is a messenger carrying grains, sculpted under a different sun. Grains that whisper of other worlds. Each particle is a relic of a system far away, caught in our instruments for only a brief moment before drifting back into the void. Light bouncing off the comet's coma carried strange fingerprints, suggesting dust clumped or coated in unusual ways. Polarization is one of those subtle tricks of physics that reveals far more than it seems. When light waves scatter off particles, whether water droplets in Earth's sky or grains of dust in space, their vibrations align in particular directions. By measuring that alignment, astronomers can deduce details about the particles themselves, their size, their shape, even their texture. It is like shining a flashlight across a surface and reading not just the reflection, but the hidden structure of what caused it. For most comets in our solar system, polarization measurements fall within a predictable range. They show patterns that confirm what we already know, that cometary dust is a mixture of silicates, organics, and tiny carbon-rich grains, loosely packed and irregular in shape. But when astronomers turn their polarimeters toward Atlas, the results refuse to conform. Instead of the gentle polarization curve typical of comets, Atlas displayed something extreme. A deep negative branch, sharper and stronger than any measured before. Such a signal suggests something unusual about the dust. One interpretation is that the grains are clumped together into porous aggregates. Like cosmic snowflakes, fragile clusters of tiny subgrains that scatter light in unexpected ways. Another possibility is that the grains are coated with exotic ices or organic materials, giving them reflective properties unlike anything we have studied locally. In either case, the implication is clear. Atlas's dust is not like ours. It carries textures, coatings, and arrangements that point to conditions shaped by a different stellar nursery. To visualize this, imagine holding two handfuls of sand. One contains ordinary beach sand, rounded grains, familiar and smooth. The other contains volcanic ash, fine, jagged, and clumped. Shine light on both, and the reflections differ dramatically. So it is with Atlas. Its dust reflects a world we do not know, a chemistry we have not lived with. The mystery deepens because polarization depends not only on composition, but also on history. How dust grains collide, stick, and fracture in a protoplanetary disk determines how they scatter light billions of years later. Atlas's strange signature may therefore be more than a chemical curiosity. It may be a fossil record of the processes that shaped its star system long ago. Perhaps collisions were gentler there, producing fluffier grains, or perhaps its parent star bathed the disk in radiation that altered surfaces, coating them in carbon-rich residues. Every hypothesis links back to a story of another world's birth. What makes polarization so powerful is that it is invisible to the naked eye. When we look at Atlas through a telescope, we see only a faint haze, but with the right instruments, that haze becomes a code. The strange polarization curve is like a fingerprint, unique to this comet, whispering truths across light years. For astronomers, the challenge now is to interpret the signal correctly. Models are being refined, simulations run, laboratory experiments designed to replicate what Webb and ground-based telescopes are seeing. Could aggregates of dust under exotic conditions reproduce the same polarization? Every answer requires careful work, but the process is already reshaping how we think about interstellar dust. And for the dreamer, there is wonder in knowing that even the light itself carries secrets. Every photon that strikes a detector has traveled across millions of kilometers, bounced off particles forged in another system, and arrived with a twist. A subtle alignment that says, "I'm not from here." Atlas's coma, in its polarization mysteries, becomes a voice of another world, speaking in the language of light. Perihelion looms in late October 2025. As it draws closer, more secrets will surface, then fade forever as the comet retreats into the void. Every comet's life in the inner solar system is a fleeting performance. It begins faint, a barely detectable smear of light. Then, as the sun's warmth breathes life into the frozen nucleus, activity accelerates. A coma swells, a tail unfurls, and chemistry locked away for billions of years is suddenly released in luminous plumes. But the spectacle is temporary. Once the comet swings around the sun and moves outward again, its brilliance dims. The gases freeze, the dust settles, and the visitor slips once more into silence. For Atlas, this drama unfolds on a schedule we can map with precision. Right now, in mid-2025, it is inbound, brightening steadily. Each passing week brings it closer to the sun, and with that closeness comes new activity. What was once dominated by carbon dioxide may soon shift. Water, hidden in deeper layers, may awaken as the sunlight grows stronger. By September, the comet will likely become a prominent target for both professional observatories and dedicated amateurs. Its tail lengthening, its coma thickening. The pivotal moment arrives on October 29th, 2025. That is perihelion, the instant when Atlas reaches its closest approach to the sun. At that moment, its activity will likely peak. Gases will erupt in force, jets may sculpt the coma into asymmetric shapes, and its chemical fingerprint may change dramatically. For astronomers, perihelion is the climax of the story, the moment when instruments must be trained on the comet without fail. The sun's glare can overwhelm telescopes, and the intensity of solar heating may fracture the nucleus, creating unpredictable outbursts or even catastrophic breakup. If Atlas survives, the outbound journey will provide further insights. By November, as it begins to recede, the comet will cool, and its emissions will fade. Comparing inbound and outbound measurements will help scientists understand how its chemistry evolves under solar influence. Did the water ever emerge? Did the dust signature change? Did the comet alter its appearance after the stress of perihelion? By December, however, the window begins to close. The comet will slip into dimness, too faint for most instruments, leaving only the archival data. After that, it will retreat into the dark, accelerating on its hyperbolic path, bound for interstellar space once more. We will never see it again. The months between now and then are all we have, a countdown ticking steadily toward finality. This is why astronomers speak of urgency. Observatories worldwide are scheduling campaigns, coordinating across continents and wavelengths, ensuring that no piece of the comet's fleeting story is lost. Every hour of observation is precious. Every spectrum, every image, every polarimetric reading adds to the mosaic of knowledge. For future generations, these records will be all that remain of Atlas, once it vanishes into the galactic night. For us, Watching this timeline unfold is both exhilarating and sobering. We know the visitor's arc. We know the milestones ahead. Brightening in September, climax in late October, fading in December, disappearance forever. It is like watching a cosmic play with a script already written. And yet, within that script, countless details remain unknown. Surprises will come, unexpected jets, sudden changes in brightness, chemistry that refuses to conform. And then, as quickly as it arrived, it will be gone. Another interstellar emissary, passing briefly through our neighborhood, leaving us with only memories and data. The timeline ahead is short, fragile, and final. But within those few months lies the chance to glimpse another world story, written in ice and dust, illuminated by our sun one last time before the void takes it back. Unlike comets from our solar system, this one will not return. Once gone, it will drift silently into the galactic night. Most comets we know are bound to the sun. They emerge from the Oort cloud or the Kuiper belt, fall inward on elongated ellipses, flare with activity as they near perihelion, and then retreat into the darkness, only to repeat the cycle centuries or millennia later. In this way, comets feel like old friends, predictable wanderers that return on schedule, weaving themselves into the story of generations. But Atlas is different. Its trajectory is hyperbolic, not elliptical. That means it is not tethered to the sun's gravity. It will not circle back. It is a passerby, here only once, then gone forever. Astronomers can plot its inbound leg, predict its closest approach, and follow its retreat, but beyond that, its fate is sealed. It will accelerate away, dwindling to invisibility, then slip beyond the edge of our solar system, bound once more for the interstellar void. There is something poignant in this, to know that we are granted only a fleeting glimpse, a single chance to learn from this visitor, before it vanishes into eternity. Humanity will never see it again. The instruments we aim at it now are our only connection to its alien origin. Once it passes, the trail grows cold. Its chemistry, its dust, its nucleus, all will be gone, unmeasurable, unrecoverable. And yet, while we cannot follow, we can imagine its path. Picture Atlas soaring outward, past the orbits of the outer planets, past the scattered disk, past the Oort cloud's icy boundary. Beyond lies interstellar space, dark, silent, and endless. There, it will continue drifting for millions, perhaps billions, of years. It may wander near another star system one day, just as it wanders near ours now. Or it may roam alone in the void, unseen and forgotten, until the end of time. Its one-way journey reminds us of scale. Our solar system, vast as it feels, is but a tiny pocket of the galaxy. To Atlas, this is only one stop along a path too long for us to grasp. It was flung outward from another system ages ago, perhaps during the birth of planets, perhaps in a gravitational dance with a giant world. Now it passes us briefly, before being cast outward once again, back into the darkness. For astronomers, this uniqueness is both thrilling and frustrating. Atlas offers the chance to study material from another star system, yet only once. No spacecraft can catch it. No mission can retrieve samples. We are left with a brief observational window, a moment of clarity, followed by an eternal absence. And for us, beyond the science, there is poetry in the thought. This is a traveller on a journey without return, a cosmic exile, wandering between suns. It carries within it the story of its home, but it shares that story only in passing, like a whisper on the wind. When it leaves, it will take its silence with it. Perhaps that is why objects like Atlas capture the imagination so deeply. They remind us of impermanence. They remind us that the universe is not static but flowing, with visitors who pass through once and never again. And they remind us, most of all, that in the vastness of space, every encounter is precious. Each interstellar object is more than a curiosity. It is a frozen message from another world, a sample we cannot otherwise reach. In many ways, comets are time capsules. Within our solar system, They preserve the chemistry of its earliest days when dust and ice swirled in the newborn sun's protoplanetary disk. By studying their compositions, scientists learn what ingredients were present at the dawn of Earth, and by extension, what conditions made our planet habitable. But interstellar comets like Atlas go one step further. They are not merely time capsules of our own beginnings. They are fragments of someone else's beginnings. Pieces of alien star systems, born under different suns, carrying their own chemical histories. That is why their study matters so deeply. We cannot yet send spacecraft to other stars. Even our fastest missions, like Voyager and New Horizons, would take tens of thousands of years to reach the nearest planetary system. For now, interstellar space is beyond our reach. But nature has delivered these objects to us, flung across light years by the gravitational chaos of distant worlds. To ignore them would be to close the door on knowledge offered freely, however fleetingly. Every molecule that sublimates from Atlas is a clue. Is its chemistry similar to our comets, suggesting common building blocks across the galaxy? Or is it radically different, pointing to exotic conditions we have not imagined? Its dust, too, tells a story. The grains are relics of collisions and condensations in its home system, fossilized whispers of how planets there were built. Even the way its tail curves under the pressure of sunlight and the solar wind reveals how fragile or compact its particles are. All of it is data. All of it is meaning. And beyond the science, there is perspective. Studying interstellar visitors forces us to confront the reality that our solar system is not the template for all others. We often fall into the habit of assuming that what we see here, water-rich comets, rocky planets near the star, giant planets farther out, is the rule. But Atlas, Borisov, and Oumuamua challenge that assumption. They remind us that diversity is the true rule of the cosmos. Every system writes its own story, and only by studying their messengers can we begin to appreciate the variety. The importance is not only academic. Understanding interstellar objects also touches on one of humanity's greatest questions. Are we alone? If life requires certain conditions, then knowing how common those conditions are across the galaxy is crucial. If so, perhaps the seeds of life are widespread. Or are most systems like the one that made Atlas, rich in carbon dioxide but poor in water? If that is the case, life might be rarer, or at least different from what we expect. These visitors, in their chemistry, may hint at how common habitable worlds truly are. And then there is wonder. To gaze at Atlas is to look not only at a comet, but at a messenger from another star. It has drifted for untold ages, silent and unseen, until it brushed past our sun. Now, for a brief season, it reveals itself, letting us measure, analyze, and dream. When it leaves, we will not see it again, but the knowledge we gain, the frozen message it carries, will remain. This is why we study visitors, not for spectacle, though their beauty is undeniable, not for fear, though their strangeness is profound, but for connection. Each one is a link across the gulf between stars, a reminder that we are part of a galaxy alive with motion, diversity, and story. And when we listen carefully, they speak not in words, but in spectra, dust, and light, telling us that the universe is wider, stranger, and richer than we have ever imagined. Long and strange, it lacked a tail, yet accelerated unnaturally. Some wondered if it was natural or something more. Oumuamua entered our solar system in October 2017, and its very name, Hawaiian for a messenger from afar arriving first, captured the awe it inspired. At first glance, astronomers assumed it was a comet, or perhaps an asteroid. It was small, only a few hundred meters in length, and faint, detectable only with the most powerful telescopes. But within weeks, it became clear that Oumuamua was something unlike anything we had ever seen. Unlike a comet, it showed no tail, no coma of gas or dust. The sun's heat did not seem to produce the outgassing we expect from icy bodies. Yet, against all odds, it accelerated slightly as it moved away. This non-gravitational push was unmistakable, but its cause was not. If it was not gas venting, what was it? The mystery deepened when astronomers tried to model its shape. Based on its brightness fluctuations, Oumuamua appeared to be tumbling, not spinning smoothly like most asteroids. Its form was elongated, perhaps 10 times longer than it was wide, either a cigar-shaped fragment or a flattened, pancake-like shard. Both interpretations strained credibility. No known natural process was expected to create such proportions, and yet, there it was, drifting through our skies. Speculation spread quickly. Some argued that Oumuamua was simply a fragment of a disrupted planetesimal, a shard of rock and metal ejected during the birth of another system. Others suggested it was a piece of frozen hydrogen or nitrogen, sublimating invisibly to produce the subtle acceleration. Still others wondered aloud if it was something artificial, perhaps a derelict spacecraft or a fragment of alien technology, its reflective surface catching sunlight like a solar sail. Among the most vocal was Harvard astronomer Avi Loeb, who proposed that the unusual shape, the lack of a tail, and the unexplained acceleration might be consistent with a thin, flat object designed to harness starlight. His ideas were controversial, sparking fierce debate within the scientific community. Most astronomers leaned toward natural explanations, preferring caution over speculation. But the fact remained, Oumuamua defied easy categorization. What made the mystery especially frustrating was the timing. Oumuamua was discovered only after it had already passed its closest point to the Sun. By the time instruments were trained on it, it was already on its way out, fading fast. Within weeks it grew too dim for detailed study, leaving scientists with only a handful of observations and far too many unanswered questions. Its legacy, however, is immense. Oumuamua proved beyond doubt that interstellar objects do visit our solar system. It shattered the assumption that our skies belonged only to local debris, and it reminded us that the universe is full of surprises, some so strange they challenge the very boundaries of what we call natural. Even today, Oumuamua lingers in scientific literature and public imagination alike. Was it a comet without a tail? An exotic shard of alien ice? Or a relic of technology drifting between the stars? We may never know. What we do know is that it opened a new chapter in astronomy, one that Atlas and Borisov have continued to write. Oumuamua's mystery endures, not just because of what it was, but because of what it represented. The moment humanity realized we are not isolated, that fragments from other stars do find their way here, carrying with them questions we are only beginning to ask. Unlike Oumuamua, Borisov looked and acted like a typical comet, comforting in its similarity to our own icy wanderers. When amateur astronomer Gennady Borisov spotted the faint streak of light in August 2019, few could have predicted the significance of his discovery. Just 2 years after Oumuamua had startled the scientific community with its bizarre behavior, here was another interstellar visitor, this time bearing all the hallmarks of a comet. Its designation became 2I divided by Borisov, marking it as the second known interstellar object and the first to clearly display a glowing coma and a trailing tail. The relief among astronomers was palpable. Oumuamua had raised unsettling questions, its strange shape, its lack of a tail, its unexplained acceleration. Some even whispered about alien technology. But Borisov was different. It behaved exactly as expected. As it approached the Sun, it began to sublimate, releasing gases and dust in the familiar pattern of comets we've studied for centuries. Its coma grew, its tail lengthened, and telescopes around the world captured images of a comet that could have easily been mistaken for one of our own. Spectroscopic analysis confirmed the impression. Borisov contained water vapor, carbon monoxide, and cyanide compounds, just as many solar system comets do. Its dust grains, too, matched the scattering properties of comets long catalogued by observatories. In many respects, Borisov seemed ordinary, almost comfortingly so. For scientists unsettled by the mystery of Oumuamua, Borisov was a reassuring reminder that interstellar comets could, indeed, resemble the icy wanderers we know. And yet, even in its familiarity, Borisov carried differences worth noting. Its carbon monoxide levels were unusually high, suggesting it formed in a particularly cold region of its home star's disk. In fact, some researchers propose that it may have originated in the outskirts of a red dwarf system. where lower temperatures allowed carbon monoxide to freeze in abundance. That detail, while subtle, offered profound insight. Its discovery also highlighted the power of human observation. Unlike Oumuamua, which was found by automated survey systems, Borisov was discovered by an individual scanning the sky with a telescope he built himself. In an age of vast data pipelines and artificial intelligence, it was a reminder that curiosity and persistence still have their place in astronomy. Gennady Borisov's dedication gave humanity a second look at the galaxy's drifting emissaries. For months, Borisov was watched closely. The Hubble Space Telescope captured it in exquisite detail. Ground-based observatories tracked its activity, measuring its brightness and analyzing its spectrum. Unlike Oumuamua, which slipped away too quickly for deep study, Borisov provided an extended opportunity. Astronomers were able to monitor it inbound, through perihelion in December 2019, and outbound until it finally grew too faint in early 2020. By then, Borisov had etched its place in history. It was the comet that confirmed Oumuamua was not a fluke, that interstellar visitors were not one in a million oddities, but part of a larger reality we had only just begun to notice. It was the comet that proved other star systems send us icy wanderers much like our own. And it was the comet that taught us, even in its ordinary appearance, that the galaxy is vast enough to hold both the familiar and the strange. Borisov was, in many ways, a cosmic reassurance. It told us, the universe is full of mysteries, yes, but sometimes it is also full of echoes, patterns, and kinship. In its tail, glittering faintly against the dark, we saw not an alien riddle, but a reflection of ourselves. Neither bizarre rock nor familiar comet. Atlas walks the line, rewriting what we thought we knew about cometary chemistry. Where Oumuamua was enigmatic and Borisov reassuring, Atlas seems to live in the middle ground, embodying traits of both while refusing to fit neatly into any category. From a distance, it looks like a comet. It has a coma. It has a tail. It brightens as it approaches the sun, behaving in ways we expect from icy wanderers. And yet, as instruments probe deeper, its secrets unravel into strangeness. Its gases, its dust, its polarization all point to chemistry unlike anything we've recorded before. This balance between the familiar and the alien is what makes Atlas so compelling. For astronomers, it is easier to dismiss an outlier like Oumuamua. Strange enough that we can chalk it up to chance, a one-off fragment of something unusual, and it is comforting to accept Borisov as proof that interstellar comets can resemble our own. But Atlas complicates the picture. It is not so strange as to be dismissed, nor so ordinary as to be easily explained. It lives in the tension between categories, and in that tension, it forces us to rethink what we believe is normal. The chemistry is the clearest example. Instead of water vapor driving its activity, Atlas spews carbon dioxide in overwhelming abundance. Its ratio 8:1 is unheard of among local comets, and the dust it sheds, when studied with polarimetry, reveals scattering behaviors that don't match our catalogues. These are not subtle deviations, they are fundamental differences. It is as if Atlas is telling us that the building blocks of other solar systems are not just variations of our own, but sometimes entirely different recipes altogether. Yet the comet's appearance is undeniably comet-like. Through telescopes it glows softly, its tail unfurling across the sky like so many icy travellers before it. Amateurs who look upon it will see a ghostly cousin of the comets they've tracked for years. In this way, Atlas bridges the gap between familiarity and alienness. It is not a riddle so baffling that we can't recognize it, but it is not a replica either. It is both. And in that balance lies its power. This in-between nature also challenges our assumptions about planetary systems. If Oumuamua, Borisov, and Atlas represent 3 points on a spectrum, then the truth is that interstellar objects may be as diverse as the stars themselves. Some will be rocky fragments, odd and elusive. Some will be icy comets, ordinary in their composition. And some, like Atlas, will sit in the middle, familiar in silhouette, alien in substance. To study them is to sketch the outline of a broader galactic diversity, one far richer than we imagined. Atlas also teaches humility. For decades, our understanding of comets was built on the assumption that our solar system was representative of the cosmos. We believed that what we saw here, water-rich comets with predictable chemistries, was a fair standard. But Atlas stands as a quiet reminder that our system is just one example among billions. The universe is not obligated to follow our rules. And perhaps that is the deeper lesson. By existing in between categories, Atlas reveals the limits of those categories. It reminds us that nature rarely draws sharp lines. The cosmos is not neat, but varied, messy, and endlessly surprising. We want to sort comets into bins, ordinary or strange, local or interstellar. But Atlas shows us that reality is more fluid. In its soft glow, stretching across the black, we see a messenger that is neither comfortingly familiar nor wholly alien. It is something else, something in between, and that in-between space is where discovery lives, where old ideas give way to new, and where the universe whispers that it is far stranger and far more beautiful than we ever dared to expect. Speculation inevitably arises. Some suggest technology, yet the evidence still points to a natural, though extraordinary, comet. It seems inevitable that when something from beyond our solar system appears, questions of artificial origin surface. After all, to witness a body arriving from the stars is to confront the unknown, and the unknown often invites wonder and suspicion. Oumuamua ignited this discussion most intensely. Its elongated shape, its lack of a tail, and its mysterious acceleration led some to propose that it could be a probe, a relic of alien engineering. Harvard astronomer Avi Loeb was among those who argued the case, suggesting that Oumuamua might be a solar sail, a wafer-thin craft propelled by starlight. So when Atlas arrived, the question returned, could this too be a piece of technology drifting between the stars? After all, its chemistry is unusual, its dust strange, its behavior unlike our comets. If nature can be so surprising, could intelligence not also play a role? But here, the evidence leans firmly toward natural origins. Atlas has a coma, it has a tail, it sublimates gases in patterns consistent with volatile ices being heated by the sun. While its composition may be unusual, nothing requires an artificial explanation. Its activity is chaotic and asymmetric in ways that match natural comets, not the precision of machinery. It looks, in short, like a comet, just one born under different conditions. That said, the speculation itself is valuable. By asking whether interstellar visitors could be artificial, we expand the boundaries of our inquiry. We remind ourselves to remain open to possibilities, even extraordinary ones. In science, skepticism and imagination must walk together. The imagination asks, what if? The skepticism answers, show me the evidence. With Atlas, the evidence tells us we are looking at an exotic natural object, but the act of questioning keeps us alert to the unexpected. And there is a deeper point here. The very fact that interstellar comets exist at all is a profound connection. Whether natural or artificial, they remind us that the galaxy is not empty. Matter flows between stars. Systems share fragments. What begins in one nursery may end up, millions of years later, brushing past another. That traffic of material makes the galaxy feel smaller, more interconnected, even without the hand of technology guiding it. Yet we cannot dismiss the cultural pull of the alien hypothesis. Human beings are storytellers, and the notion of visitors from the stars resonates deeply with us. Science fiction has long imagined derelict craft, probes, or messages drifting between suns, so when a comet behaves strangely, it is only natural that we project those stories onto it. In the case of Atlas, the truth is more grounded, but no less wondrous. For what is more extraordinary than a natural object carrying the fingerprints of another star system across light years, arriving unannounced in our skies? So, could Atlas be alien? In the sense of technology, almost certainly not. In the sense of origin, absolutely yes. It is alien in the truest form. A product of another world, born under a different sun, shaped by conditions we have never experienced. Its strangeness is not artificial, it is cosmic. And perhaps that is even more compelling. Technology we could eventually understand, but nature, in its infinite creativity, will always find ways to surprise us. Atlas stands as proof. We need not look for extraterrestrial machinery to find wonder. The universe itself, in its natural diversity, is wondrous enough. Harvard astrophysicist Avi Loeb offers a framework ranking objects from certainly natural to possibly artificial. Atlas scores low but not zero. The question of whether interstellar objects could ever be artificial remnants of alien technology has gained traction in recent years, in large part because of Oumuamua's strange behavior. Avi Loeb, known for both his bold hypotheses and his willingness to stir debate, has suggested that science should not shy away from such possibilities. In his view, when something unexplained appears in the sky, dismissing the idea of intelligence outright is as unscientific as leaping to it without evidence. To help guide the conversation, Loeb has proposed a kind of informal scale, one that arranges objects along a spectrum, from certainly natural to potentially ambiguous to plausibly artificial. At the low end are the familiar asteroids and comets whose compositions and orbits match what we understand from centuries of study. At the high end would be objects showing signatures that defy natural processes, perfect geometric shapes, unusual trajectories powered without visible forces, or repeating signals. Oumuamua, with its lack of a tail, its cigar or pancake-like shape, and its unexplained acceleration, earned a spot closer to the ambiguous middle. To Loeb, it was not proof of technology, but it raised enough oddities to merit serious consideration. That suggestion sparked controversy, with many astronomers pushing back, offering natural explanations. Yet Loeb's scale gained attention because it framed the debate in a way the public could follow. Where then does Atlas fall? Despite its unusual chemistry, Atlas fits comfortably toward the natural end of Loeb's spectrum. It shows a coma. It shows a tail. Its behavior aligns with the sublimation of volatile ices. While it defies expectations with its carbon dioxide dominance and peculiar dust, these traits are variations within the cometary family, not departures from it. In Loeb's language, Atlas scores low on the artificial scale, unlikely to be anything but natural. Yet, importantly, not zero. And that is the nuance Loeb emphasizes. Until we understand the full range of what nature can produce, there will always be a sliver of uncertainty. Anomalies demand explanation, and until they are explained, they leave room, however small, for speculation. Atlas may not stretch the imagination in the way Oumuamua did, but it still teaches us to keep an open mind. The strength of Loeb's framework is not that it proves anything artificial exists, but that it legitimizes curiosity. It encourages astronomers to document oddities carefully, to resist the temptation to file away anomalies as mere noise. In this sense, the scale is less about aliens and more about humility. A reminder that our models are not complete, and that the universe is often stranger than we think. For Atlas, the score is reassuringly natural, yet the very act of scoring it forces us to engage with a profound question. How would we recognize technology if we saw it? Would we know the difference between a comet shedding exotic ices and a probe designed to mimic one? Would we distinguish a fragment of alien geology from alien engineering? These are not idle musings. They are tests of our readiness to interpret what the universe may one day present to us. So while Atlas is almost certainly a natural comet, its place on Loeb's spectrum is still meaningful. It reinforces the idea that we must look carefully, question honestly, and remain open to possibilities without rushing to extraordinary conclusions. The galaxy is vast, its surprises endless. To close our minds would be to miss its messages, whether written in the chemistry of a comet, or perhaps, someday, in something more. Webb breaks light into rainbows. Each molecule leaves its mark. Reading Atlas is like scanning the barcode of an alien nursery. When we look at a comet through an ordinary telescope, we see beauty, a glowing coma, a trailing tail, the shifting shimmer of sunlight on icy dust. But beauty alone does not reveal the details of chemistry. To peer deeper, astronomers use spectroscopy, a technique that splits light into its component colors, just as a prism turns white light into a rainbow. Instruments like Webb's near-infrared spectrograph break the comet's glow into precise bands of wavelength. Within those bands, molecules announce themselves. Each chemical compound absorbs and emits light in unique ways. Water vapor leaves a set of dark absorption lines. Carbon dioxide, methane, and carbon monoxide carve their own distinct patterns. The result is like a barcode in a supermarket, where each black stripe encodes a number. For astronomers, each line in a spectrum encodes a molecule, and by reading those lines, we can tell what the comet is made of without ever touching it. For Atlas, this barcode was unlike anything seen before. Instead of the water-rich spectrum expected from comets, Webb found a signature dominated by carbon dioxide. Its barcode leaned heavily toward exotic volatiles, with faint traces of water lurking far in the background. That single scan told scientists more than weeks of imaging ever could. It revealed a comet not only active, but chemically alien. The metaphor of a barcode is apt in another way too. It allows quick comparison. When astronomers line up the barcodes of comets from our solar system, patterns emerge. Most look broadly similar, dominated by water, with supporting peaks from carbon-based molecules. Borisov, the second interstellar visitor, fit neatly into that pattern, its barcode reassuringly familiar. Its barcode defied the template. One glance revealed that this comet was stamped with a different origin. The beauty of spectroscopy is that it not only reveals what is present, but how much. By measuring the strength of each line, astronomers can calculate ratios. Carbon dioxide to water, carbon monoxide to cyanide, dust to ice. These ratios are fingerprints of a comet's birthplace. They reveal the temperatures, pressures, and radiation fields under which it formed. Reading Atlas's spectrum is, quite literally, reading the environmental history of another solar system. It is worth pausing to consider how extraordinary this island humanity cannot yet send probes to distant stars. We cannot scoop ice from alien comets or drill into their cores, and yet, with light alone, we can know their chemistry. A single photon, absorbed by an alien molecule billions of years ago, re-emitted and carried across light years, lands in Webb's detectors and whispers, "I was carbon dioxide." Multiply that by millions of photons, and suddenly an alien world's story is told in full. Spectroscopy transforms a faint smudge into a voice. Without it, Atlas would be just another comet with an odd tail. With it, Atlas becomes a messenger from an alien nursery, its barcode revealing the frozen recipe of a star system we will never visit. That barcode tells us Atlas was born in conditions colder, stranger, and richer in carbon dioxide than ours. It tells us diversity is the rule, not the exception. In that sense, spectroscopy is more than a tool, it is a bridge. A way of connecting our instruments here with environments light years away. Each spectrum is a thread across the void, linking us to nurseries under alien suns. And in the barcode of Atlas, we read a story not of ourselves, but of another place entirely. Dust tells a quiet story. Its odd scattering suggests Atlas carries compounds or structures not found in our solar system. When we imagine comets, we often picture glowing tails of ice sublimating in sunlight. But just as important as the gases are, the grains of dust, the rocky crumbs and carbon-rich flecks carried away from the surface. Each particle is a fragment of the comet's core, preserved since the dawn of its birth. Studying dust is like examining the handwriting of a planetary system, with every grain marking the conditions of its formation. For Atlas, the dust has proven as intriguing as the gases. When astronomers studied the way its coma scattered sunlight, they found signals that defied expectations. The light was polarized in unusual ways, hinting that the grains are not smooth, simple particles, but irregular, perhaps clumped into fluffy aggregates or coated with exotic ices. Such scattering patterns have no exact counterpart in comets we have studied from our own system. They point toward dust with alien textures born in an environment where different chemical recipes and physical conditions shape their form. Dust, after all, is not inert. It records history. If grains are porous, they may have formed in cold, low-pressure regions where gentle sticking dominated. If they are coated in organics, radiation from the parent star may have altered their chemistry, baking in complex hydrocarbons. If they clump into fragile aggregates, the collisions that built them were likely less violent than those in our own solar nursery. Each interpretation tells a different story about the star system Atlas once called home. Another clue lies in colour. Dust scatters light differently depending on its size and composition. Some comets produce dust that reflects sunlight with a reddish hue, others with a bluish tint. Atlas seems to lean toward the unusual, reflecting light in ways that suggest either carbon-rich surfaces or grains altered by radiation, unlike the Sun's. Perhaps it formed around a smaller, dimmer star, a red dwarf whose spectrum left chemical imprints we are only now decoding. Even the size distribution of the grains matters. Smaller particles are swept easily into long tails by solar radiation, while larger grains stay closer, forming trails of debris. By measuring how Atlas's tail develops, astronomers can estimate the grain sizes it sheds. Already, it seems that the comet favours dust of unusual fineness, grains that scatter light in ways not seen in our local comets. This too suggests differences in the physical processes of its origin system. And dust does more than reveal the past, it shapes the future. Some of the grains escaping Atlas will drift into interplanetary space, potentially intersecting Earth's orbit in years to come. If they do, they may appear as faint meteors, burning briefly in our skies. Should such an event occur, it would mean that fragments of an alien star system had literally entered our atmosphere, glowing for a heartbeat before turning to vapor. The thought alone is humbling, the dust of another sun falling into our night. For scientists, the study of Atlas's dust is painstaking. Spectroscopy, polarimetry, and direct imaging must be combined to tease out its secrets. The goal is not simply to catalogue differences, but to understand their meaning. Why do Atlas's grains behave so oddly? What does that say about its star system's chemistry, its collisions, its radiation environment? Each answer enriches our broader picture of how planetary systems vary across the galaxy. In the end, the dust is a quiet messenger. Unlike the dramatic plumes of gas, it does not shout. But in its subtle scattering, in its silent drift through space, it tells us that Atlas is no ordinary comet. It is a stranger carrying fragments shaped in a nursery. We will never see an alien story written in particles too small to touch, but large enough to transform our understanding of the universe. Machines like Atlas, Pan-STARRS, and Vera Rubin Observatory sweep the skies relentlessly, finally catching what once slipped away. For most of human history, interstellar visitors would have passed unnoticed. Comets flared briefly, were recorded in chronicles, and then disappeared into myth. Only in the past century did astronomy begin to turn systematic, with photographic plates and dedicated sky surveys cataloguing faint smudges of light against the stars. Most of the sky remained unmonitored, and faint, fast-moving objects could slip by undetected. The turning point came with robotic surveys. The ATLAS system, Asteroid Terrestrial Impact Last Alert System, was designed to scan the skies every night for potential threats to Earth. Pan-STARRS in Hawaii, with its massive digital cameras, added another sweeping eye, capable of recording millions of stars, galaxies, and asteroids in a single shot. Together, these machines transformed astronomy from reactive to proactive. Instead of stumbling upon comets by chance, we began to expect them, to anticipate their arrival. And now comes the Vera C. Rubin Observatory in Chile, a facility designed to take this transformation even further. Its large synoptic survey telescope will photograph the entire visible sky every 3 nights, creating a dynamic map of the heavens in unprecedented detail. With it, faint visitors like Oumuamua, Borisov, and Atlas will no longer slip quietly past. Instead, they will be caught early, tracked, and studied with a precision once impossible. This shift is revolutionary. For the first time, we can build timelines of discovery that align with opportunity. Oumuamua, found too late, faded before its secrets could be probed. Borisov, discovered inbound, offered months of observation. Modern surveys turn luck into certainty, giving us windows to study objects we once only dreamed of. But beyond catching rare interstellar objects, these surveys are changing how we see the cosmos itself. They reveal the restless sky. Asteroids tumbling, stars flaring, galaxies colliding. They show us that change is constant, that the heavens are not fixed but alive with motion. Every night, terabytes of data flow into archives, each frame a snapshot of the universe in action. Within that flood, software hunts for anomalies, the streak of a comet, the flash of a supernova, the wander of an asteroid. For scientists, the challenge now is not finding but interpreting. Machine learning sifts through the torrents of images, flagging what might matter. Human astronomers then step in, prioritizing targets, allocating telescope time, deciding which faint dot might hold the key to discovery. In this way, the partnership between human curiosity and machine persistence has become the heartbeat of modern astronomy. And yet, there is something poetic in the thought that machines are now our sentinels. When dawn comes, they present us with their findings. Another asteroid, another flare, another visitor from the stars. In them, the ancient desire to map the sky finds its modern expression. Without Atlas, Pan-STARRS, and soon Vera Rubin, Atlas might have passed unnoticed, a ghost slipping by in silence. Instead, we caught it, studied it, and learned from it. Modern surveys have given us the gift of awareness, turning the chance arrival of interstellar objects into opportunities for science, wonder, and reflection. In the quiet glow of their nightly sweeps, these machines remind us that discovery is no longer bound by chance. It is a matter of vigilance, of persistence, of eyes that never close, and through them, the cosmos reveals what it has always held: stories waiting to be seen. 3 in less than a decade. Perhaps these visitors are not rare, just rarely noticed. Perhaps they've always been here. Before 2017, the idea of spotting an object from another star system felt almost like science fiction. Then came Oumuamua, slipping silently through our skies and vanishing almost as quickly as it was noticed. Just 2 years later, Borisov appeared, this time clearly a comet, leaving no doubt that it had arrived from beyond. And now, Atlas joins the story. 3 confirmed interstellar visitors in under 10 years. A coincidence? Or a revelation? Astronomers are beginning to suspect the latter. For centuries, these wanderers likely passed unnoticed, their faint smudges lost in the clutter of stars. With telescopes limited in power and coverage, we simply had no way to find them. Now, with automated surveys scanning the sky every night, we suddenly see what was always there. Like turning on a light in a dark room, the interstellar visitors are revealed not by their rarity, but by our newfound vigilance. Estimates are evolving quickly. Early models suggested that interstellar objects might be few and far between, separated by millions of cubic kilometers of empty space. But with 3 discoveries in quick succession, scientists are revising those numbers upward. Some now argue that thousands of interstellar comets and asteroids may be drifting through our solar system at any given time, most too small or too faint to detect. If true, we are swimming in a sea of alien debris, unaware until recently of how plentiful it truly island. The implications are profound. If interstellar objects are common, then every star system in the galaxy must be shedding material constantly. When planets form, collisions and gravitational interactions fling debris outward. But some is cast free entirely, exiled into interstellar space. Over billions of years, those fragments accumulate, creating a galactic background of wanderers, silent travelers, carrying the fingerprints of countless nurseries. This perspective changes how we see our solar system. It is not an isolated island, but a crossroads. Debris from other stars passes through routinely, brushing against our sun's gravity, sometimes bright enough for us to notice. Each object we detect is not the rare exception, but the visible tip of an invisible iceberg. Beneath it lies a population vast beyond comprehension. Yet rarity is still relative. Large interstellar comets like Atlas are easier to spot, but much smaller objects may be far more common. Some might even strike Earth's atmosphere, burning up as meteors. In fact, a few unusual meteor detections have already been proposed as candidates for interstellar origin. Their speed's too great to be bound by the sun's pull. If confirmed, it would mean that fragments of alien worlds have literally fallen into our skies. unnoticed until recently. So how rare are they really? Perhaps not rare at all. What is rare is our ability to see them clearly. The past decade marks the dawn of that ability. With surveys like ATLAS, Pan-STARRS, and soon the Vera Rubin Observatory, we are finally glimpsing a reality that has existed for billions of years. Interstellar visitors have always been here. Only now are we awake enough to recognize them. And that realization is transformative. It shifts the question from, will we ever see another, to how many are passing by right now unseen. The cosmos is not silent. It is full of fragments, drifting emissaries of other suns. By finding them, we are not encountering rare miracles, but participating in the ordinary traffic of a galaxy alive with motion. How does a comet escape its star? A close brush with a giant planet could fling it into interstellar space, cast adrift forever. Every planetary system is a dance of gravity. Stars pull at planets, planets tug at asteroids, and comets wander through the outer reaches like restless ghosts. Most of these orbits are stable, held in place by the balance of attraction and momentum. But stability is not eternal. One encounter, one planetary near miss is enough to change everything. For a comet, the difference between being bound to a star forever and being exiled into the galaxy often comes down to a single gravitational kick. Picture a young planetary system. Giant planets loom at the edges, their immense gravity sculpting the paths of smaller bodies. When a comet drifts too close, it accelerates, slingshotting around the giant's mass. Depending on the angle, the encounter can either trap the comet into a tighter orbit or fling it outward at escape velocity. If the push is strong enough, the comet breaks free not just from the planet's grasp, but from the star itself. No longer bound, it sails into interstellar space, never to return. This process is not rare. In fact, it likely happened in our own solar system. Astronomers suspect that during the early days of planetary formation, Jupiter and Saturn scattered trillions of icy bodies. Most were corralled into the Oort cloud, forming the distant shell of debris that still surrounds us. But countless others must have been ejected entirely, cast into the void between stars. Atlas, Oumuamua, Borisov. These are likely products of similar events in other systems, the inevitable debris of gravitational billiards. The mechanics are elegant. A comet approaching a giant planet gains kinetic energy from the planet's motion around the star. It is the same principle spacecraft use for gravity assists, slingshotting past Jupiter to accelerate toward the outer planets. But for comets, the effect can be final. With the right trajectory, the added energy lifts them past the escape velocity of their home star. Once that threshold is crossed, they are free travelers, bound no longer to any single sun, but to the galaxy itself. The timescales involved are immense. A comet ejected from a young system might wander for billions of years before encountering another star closely enough to be noticed. Most will spend their lifetimes adrift, their frozen nuclei unchanged in the cold of interstellar space. When by chance they pass near another star, our Sun, for example, they briefly awaken, shedding light, dust, and secrets before continuing their eternal voyage. What is striking is the scale of this process. If every planetary system ejects even a fraction of its comets, then the Milky Way must be filled with them. Tens of trillions, perhaps quadrillions, of frozen wanderers roaming silently through the dark. Some are as small as boulders, some as large as mountains. Most never cross paths with another star closely enough to be seen. But a tiny fraction just enough drift into our skies, where their alien chemistry can be revealed. The ejection process also hints at the chaotic beauty of planetary formation. Worlds collide, orbits shift, and debris is scattered like seeds. Some seeds remain, germinating into moons or asteroids. Others are lost to the void, carrying with them the story of their system. Atlas is one such seed, flung outward untold ages ago, only now crossing our Sun's domain. So when we watch Atlas's tail unfurl, we are not just seeing a comet. We are seeing the consequence of gravity's relentless game, played out across time and space. A comet is born, scattered, ejected, and finally glimpsed an emissary not by design but by physics. And behind its journey lies a truth. Every planetary system sheds pieces of itself, and those pieces may travel farther than the worlds that made them ever could. Though Atlas glows, it speaks no words, no signals, no transmissions, just natural chemistry, whispering the story of another system. When a comet enters our skies, it is easy to project meaning onto it. For millennia, cultures saw comets as omens, messages from the gods, heralds of change. In modern times, the symbolism has shifted, but the impulse remains. Some wondered if Oumuamua's silence hid something intentional, if its strange trajectory was not just a natural path but a choice. Others speculated about Borisov, or now Atlas, imagining them as vessels, probes, or monuments drifting through the stars. But the truth is quieter. Atlas does not transmit. It does not beam radio waves nor pulse with encoded signals. Webb's instruments, sensitive to the faintest light, detect only natural emission carbon dioxide glowing under sunlight, dust scattering photons in strange polarization curves. Its voice is chemistry, not technology. The silence of space is unbroken, save for the hum of natural processes. And yet, silence does not mean emptiness. In the language of science, Atlas speaks volumes. Its spectrum is a story. Lines of carbon dioxide dominating over water. The faint echoes of carbon monoxide, the subtle fingerprints of dust. Each tells us something about the world where it formed, the environment of its nursery. The silence is not void, it is encoded, waiting for us to learn how to listen. There is also beauty in this restraint. Imagine Atlas as a traveller who has carried its tale for millions of years, not in words but in its very body. Every molecule locked in its ice, every grain in its dust, is part of that narrative. And in that exhalation, we read the record of another world. For astronomers, this is a kind of listening. They use spectroscopy, polarimetry, imaging, and modelling to translate the silent language of nature into meaning. To the human eye, Atlas is a glowing blur. To instruments, it is a library, its silence transformed into sentences of light and chemistry. What it does not say, in transmissions, it reveals in spectra. Silence also invites humility. We are eager for messages, for signs that someone out there might be reaching out. But Atlas reminds us that not all visitors are communicators. Some are simply fragments of cosmic history, drifting on paths set by gravity, untouched by intention. And yet, they still have much to teach us. In their silence lies knowledge about diversity, about formation, about the universality of physics across stars. Perhaps one day we will hear more than chemistry. Perhaps another object will arrive that truly does transmit, or carry unmistakable signs of technology. But until then, the silence is not disappointing, it is profound. It reminds us that the universe does not revolve around us, that its motions and creations unfold regardless of our presence. We are listeners, not recipients of crafted messages, and what we hear is what nature allows. So as Atlas glows in our sky, silent but luminous, it teaches us patience. The cosmos speaks not in broadcasts but in subtle whispers. The glow of molecules, the scattering of dust, the path traced through space. To learn from it, we must quiet our expectations and listen with the tools of science. The silence of space is not empty, it is full of unspoken stories. Atlas is one of them, a fragment of another world, telling us what it can, in the only language it knows. And if we are willing to listen, even that silence becomes a kind of song. Could the glow of Atlas hint at frozen compounds rare in our system? Cyanogen, diatomic carbon, or something stranger still. When sunlight strikes a comet, it is not just a source of heat. It is a brush painting the coma and tail with colour. Most comets appear faintly white or bluish, the combined effect of dust scattering and the fluorescence of familiar molecules. But every so often, a comet takes on a distinct hue. Green, in particular, has fascinated astronomers and skywatchers alike, its emerald glow shimmering against the black canvas of space. Could Atlas, with its alien chemistry, carry colours born of ices uncommon in our solar system? The usual suspects behind cometary colour are cyanogen and diatomic carbon. These molecules, when excited by ultraviolet sunlight, fluoresce with a striking green emission. Many comets near the Sun develop this emerald halo, their comae glowing softly as the exotic gases sublimate. Yet in most cases, the glow is short-lived, fading as the molecules break apart under solar radiation. Still, even this fleeting hint is enough to transform a comet from a faint smudge into something otherworldly. For Atlas, whispers of a green glow emerged early farther from the Sun than expected. If confirmed, this would imply not only a richness in these exotic compounds, but also a structure that allows them to escape before water vapor dominates. In our comets, water usually takes center stage, overwhelming subtler emissions. But in Atlas, where carbon dioxide already eclipses water, the conditions are ripe for stranger chemistries to reveal themselves. Imagine its nucleus, a frozen mixture forged in the cold outer reaches of another system, layered with exotic ices accumulated at temperatures lower than our Kuiper belt. When sunlight touches its surface, not only does carbon dioxide vent, but cyanogen and diatomic carbon may rise in unusual abundance. The result would be a greenish hue that marks Atlas as different, its glow not merely beautiful but diagnostic of its alien birth. And what if there is more? Beyond cyanogen and diatomic carbon lie possibilities we scarcely consider. Exotic hydrocarbons, sulfur-bearing compounds, or nitrogen-rich ices could contribute subtle shades or tints we rarely observe because they are scarce in our system. Atlas may harbour frozen chemistry that, under the Sun's influence, produces spectral fingerprints unlike any we've catalogued. For astronomers, these colours are not just aesthetic, they are data, signals waiting to be decoded. Telescopes like Webb, equipped with sensitive spectrographs, can pass the light with precision, distinguishing between the familiar and the unfamiliar. A green coma would not be taken at face value but broken into its spectral components, each peak revealing the presence of molecules. Already, Webb has confirmed carbon dioxide dominance in Atlas, but if cyanogen or other exotic compounds appear in strength, they will stand out like signatures in a ledger. The symbolism of colour also matters. Throughout history, green comets were seen as omens, their glow unsettling under night skies. Today, science has stripped away the superstition, but the awe remains. To gaze upon a comet glowing emerald, knowing it carries ices from a world we will never see, is to feel a connection that transcends myth. It is a reminder that colour, even in space, is more than light. It is chemistry, history, and message combined. So, could the glow of Atlas be the colour of alien ice? The evidence suggests it is possible. Cyanogen, diatomic carbon, or perhaps stranger compounds could be the artist painting its coma. If true, the green light we see is not just a spectacle, it is a voice from another star system, encoded in photons, telling us of elements rare here but common there. Atlas glows not with words, but with colour, and in that colour lies its alien identity, a luminous bridge between worlds. Worldwide, telescopes are racing the clock, booking time slots, aiming to capture the comet before it vanishes into sunlight. Every interstellar visitor forces astronomers into a sprint. These objects are faint, fast, and fleeting, spotted only weeks or months before their closest approach, and gone forever soon after. For Atlas, the urgency is especially sharp. Its perihelion in late October 2025 marks the narrow window when the comet will be brightest, when its gases and dust will be most abundant, and when instruments can extract the richest details of its alien chemistry. Once that window closes, Atlas will dim, fading into the black, never to return. The race begins with scheduling. Major observatories, from Chile's Atacama Desert to Hawaii's volcanic peaks, must allocate time carefully. Competing projects, exoplanet surveys, galaxy studies, dark matter hunts suddenly make room for a comet that cannot wait. Astronomers submit urgent proposals, sometimes called target of opportunity requests, arguing that this is not just another icy body but an interstellar emissary. Committees weigh the rarity of the event against other priorities, and almost always the decision tilts in the comet's favour. After all, the cosmos will still hold its galaxies tomorrow. Atlas will not. Space-based instruments too must be prepared. The James Webb Space Telescope cannot simply pivot on a whim. Its schedule is booked months in advance, its fuel precious. Yet, when interstellar objects appear, Webb's planners reshuffle, carving out observing windows to capture spectra and images. Other spacecraft like Hubble and even small solar probes are also enlisted. The goal is to create a global multi-wavelength campaign. Infrared from Webb, visible light from ground-based giants, ultraviolet from Hubble, radio observations from arrays like ALMA. Together, they weave a full portrait of the visitor. On the ground, smaller telescopes also play their part. Amateurs with modest instruments track brightness changes night by night, feeding data into networks that guide the larger facilities. Robotic survey telescopes, like Pan-STARRS and Atlas itself, monitor the comet's position, refining its orbit so that precision instruments can aim without error. It is a symphony of coordination, from the largest mirrors to backyard enthusiasts, all focused on the same speck of light. Preparation is not only logistical but technical. Instruments must be calibrated to detect faint signatures against the glare of the sun, which grows stronger as the comet nears perihelion. Spectrographs are tuned for expected molecules, while still leaving room to capture surprises. Imaging systems adjust filters to study dust tails, while polarimeters prepare to probe the scattering of alien grains. Every detail matters, because there will be no second chance. And then there is the weather, always the unpredictable adversary. Even the best-laid plans can be clouded out, leaving astronomers to watch helplessly as the comet passes beyond reach. That is why redundancy is built into the strategy. Multiple observatories across continents are assigned overlapping roles, ensuring that if one site loses a night, another can carry the load. All of this preparation reflects a deeper truth. Interstellar visitors like Atlas are not just another research target. They are moments of connection, chances to glimpse beyond our solar system without leaving home. The urgency is not simply about data, it is about seizing a once-in-a-lifetime opportunity, one that will never repeat. In the coming months, as Atlas brightens, a chorus of instruments will awaken. Mirrors will tilt, detectors will hum, software will pass photons that began their journey in a different star system. For a brief season, the world's telescopes will unite in purpose, all chasing the fading trail of a cosmic wanderer. And when Atlas is gone, the data will remain. Spectra, images, light curves, polarization maps a library of an alien comet, captured in its only visit. All because, in these final weeks, astronomers prepared their instruments with care, knowing that discovery waits for no one. Its velocity is too great for capture. Earth could never hope to chase it. We are left to watch, not pursue. Comets born within our solar system move swiftly, yet their paths are predictable, bound by the sun's gravity. Spacecraft like Rosetta or Deep Impact could rendezvous with them, given enough time and clever orbital mechanics. But Atlas is different. It comes not in a graceful ellipse, destined to return, but on a hyperbolic arc and escape path. Its speed, nearly 60 kilometers per second relative to the sun, places it forever beyond capture. By the time we see it, it is already rushing past, too fast for us to follow. This speed is not an accident, but the natural outcome of its origin. To be here at all, Atlas had to be ejected from its home star system with enough velocity to overcome stellar gravity. That required the gravitational slingshot of a giant planet or a close encounter during its system's chaotic youth. For millions of years, perhaps billions, it drifted in the void, carrying that excess speed with it. Now, as it cuts through our solar system, it simply continues its journey, unbound and unstoppable. For Earth, this velocity means limitation. Space agencies have dreamed of intercepting interstellar objects, even designing mission concepts, but the practical challenge is immense. To chase Atlas would require not only predicting its path early, but also launching a spacecraft capable of extraordinary acceleration, something far beyond our current chemical rockets. Even ion drives and solar sails, promising though they are, would struggle to catch a comet moving this fast. Timing is everything, and Atlas gave us little notice. Oumuamua, too, was lost to speed. Discovered only after perihelion, it was already fading, impossible to catch. Borisov, though more cooperative, still outran any realistic mission. Atlas continues the pattern, reminding us that interstellar visitors will always be fleeting. To meet one with a probe will require either luck catching it inbound years before perihelion or readiness, with spacecraft standing by, waiting to launch the moment another appears. Speed also changes how we observe. Because Atlas moves so quickly across the sky, astronomers must coordinate to track it continuously. In a single night, its position shifts enough to require constant adjustment. This demands precision scheduling and rapid data analysis, ensuring no opportunity is lost. Observing Atlas is not a leisurely pursuit, it is a race against motion. Yet speed is also a gift. The very fact that Atlas moves so quickly confirms its interstellar nature. Bound comets never escape the sun's pull. Their paths curve back, however elongated. Hyperbolic velocity is the signature of alien origin. To watch Atlas streak through the sky is to see proof that it came from another star, carried here on momentum gained long ago. Its speed is not just a challenge, it is its identity. And in a way, speed adds poignancy to the encounter. We cannot hold Atlas. We cannot follow it. We can only observe, record, and then let it go. Its velocity reminds us of impermanence, that the most extraordinary discoveries are often the most fleeting. The comet teaches us patience but also urgency. To prepare, to watch carefully, to seize the moment before it vanishes. So why does speed matter? Because it defines the nature of interstellar visitors. It is what sets them apart, what makes them unreachable, what ensures that every encounter is singular. Speed is the reason Atlas cannot be captured, the reason we must rely on light alone to study it, and the reason it will soon be gone. For us, bound to Earth, speed is limitation. For Atlas, speed is freedom. And as we watch it blaze past, we are reminded that the galaxy is full of wanderers, too swift for us to catch, yet generous enough to share their secrets in passing. Plans once arose to chase Oumuamua. Could we one day build interceptors, ready to launch when the next interstellar visitor arrives? When Oumuamua slipped past in 2017, it left astronomers inspired but frustrated. Its trajectory was plotted, its light curves recorded, but the window for close study had already closed. For many, the thought was unbearable. Humanity had encountered its first confirmed interstellar object, and yet it vanished before we could truly know it. Out of that frustration was born Project Lyra, a concept proposed by researchers at the Initiative for Interstellar Studies. Their idea was bold: build a spacecraft capable of intercepting Oumuamua even years after its departure, catching up to it in deep space. The challenges were staggering. To pursue Oumuamua required speeds far beyond our current rockets. Concepts involved using gravity assist from Jupiter, combined with solar orbit maneuvers, dives close to the Sun to gain extraordinary acceleration. Some designs suggested using advanced propulsion methods, such as nuclear thermal engines or even solar sails, to close the distance. It was ambitious, bordering on science fiction, but it captured imaginations worldwide. For the first time, humanity seriously considered chasing a messenger from another star. Ultimately, Project Lyra could not materialize in time. By the time the proposals were detailed, Oumuamua was already too far, too faint. The opportunity was lost. But the dream did not die. Instead, it evolved. Scientists began to argue not for chasing after the fact, but for preparing in advance for building a system that could launch rapidly when the next interstellar object appeared. Enter the idea of rapid response interceptors. Instead of designing one mission for one object, the vision is to create modular spacecraft, stored and ready, able to launch within months of discovery. Powered by high-efficiency propulsion and guided by flexible mission profiles, these craft could rendezvous with an interstellar visitor during its perihelion, when it is brightest and most active. The key is speed both in the spacecraft itself and in humanity's readiness to act. The upcoming Vera C. Rubin Observatory may make this dream more plausible. With its ability to scan the entire sky every few nights, Rubin will likely detect many more interstellar objects, often years before perihelion. That lead time could be enough to launch an interceptor and meet a visitor at close range. Combined with ongoing advances in propulsion solar sails, nuclear thermal rockets, and perhaps even fusion concepts, the possibility grows less fantastical with each passing decade. Why pursue at all? Because close study could answer questions no telescope ever can. A probe could sample dust, measure magnetic fields, even photograph the nucleus directly. If Oumuamua left us puzzled, and Atlas leaves us tantalized, an interceptor mission could leave us enlightened, turning mystery into knowledge. It would be our first direct look at the building blocks of another star system, the closest humanity has yet come to interstellar exploration. The dream of Project Lyra embodies something deeply human. The refusal to let wonder pass us by. Though Oumuamua escaped, its legacy may be that it inspired us to prepare for the next. If Atlas cannot be caught, perhaps its successors will be. One day, when another visitor sweeps through, humanity may be ready not only to watch, but to pursue. For now, we remain grounded, our instruments pointed upward, our spacecraft limited by the slow crawl of current propulsion. And perhaps, in the quiet planning rooms of engineers and visionaries, the first blueprint of an interstellar interceptor already lies, waiting a promise that the next visitor will not be allowed to slip silently away. Brightness deceives. The nucleus may be far smaller than it appears, masked by gases and dust, an icy heart we may never see. When we gaze at a comet through a telescope, what we see is not its body but its atmosphere. The coma, a vast cloud of gas and dust, can swell to tens of thousands of kilometers, dwarfing the solid heart within. The nucleus, the true comet, is often only a few kilometers across, buried in a shroud of vapor and light. For interstellar visitors like Atlas, this effect is even more deceptive. To the eye, Atlas glows with activity, stretching tails across the sky. But deep inside is likely a small, fragile fragment of ice and rock, cloaked in brilliance far beyond its actual size. Measuring the nucleus directly is a challenge. Even the sharpest telescopes struggle to pierce the glare of the coma. Techniques such as high-resolution imaging, or watching brightness variations as the nucleus rotates, can provide estimates, but they remain uncertain. For Atlas, the numbers suggest something modest, perhaps only a kilometer or two, wide, maybe even smaller. If true, then the spectacle of its tail and coma is a kind of illusion, a grand performance powered by a tiny stage. This illusion speaks to the power of sublimation. When sunlight strikes the nucleus, volatile ices erupt into space, carrying dust grains with them. A handful of gas molecules becomes a fountain becomes a cloud, and soon the nucleus is buried in its own emissions. A small icy heart can masquerade as a world, its atmosphere 1,000,000 times larger than the body itself. Atlas, like all comets, is defined not by its size but by its activity. And yet, the nature of that hidden core matters deeply. Its composition tells us whether Atlas formed in a cold outer belt or a warmer inner disk. Its density hints at whether it is a fluffy rubble pile or a solid block of ice. Its rotation rate can reveal whether jets of gas are pushing it into a tumble, but these details are difficult to extract without direct imaging or a spacecraft flyby. From Earth, we see only the cloak, not the body. Speculation abounds. Is Atlas's core porous, riddled with voids like pumice stone, making it fragile against solar heating? Or is it compact, hardened by radiation during its long interstellar drift? Could its chemistry be stratified, with outer layers dominated by carbon dioxide and deeper reserves of water ice yet to awaken? Each scenario would explain its peculiar activity, but only glimpses through data can narrow the truth. There is also the haunting possibility that we may never know. Unlike local comets, which can return and offer repeated opportunities, Atlas is on a one-way journey. Once it leaves, its nucleus will vanish into the dark, never to be measured again. Without a probe to meet it, its icy heart will remain hidden, wrapped in mystery. Yet perhaps that is fitting. The nucleus of Atlas is not just an object, it is a symbol, a reminder that even the brightest phenomena may have humble beginnings, that grandeur can emerge from fragility. A single kilometer of alien ice, thrown into sunlight, becomes a beacon visible across millions of kilometers. Its brightness deceives, but its story enlightens. So when we look at Atlas, we must remember the truth. Beneath the glowing veil, beneath the expanding tail, lies a hidden core. Small, silent, and ancient. An icy heart that has travelled for ages, carrying within it the frozen memory of a star system we will never touch. And though we may never see it directly, its presence shapes everything we observe. In its silence lies the secret of its brilliance. As sunlight warms the frozen nucleus, ices sublimate, releasing plumes that build the coma and tail. But Atlas's recipe is unique. Outgassing is the beating heart of a comet. Without it, the nucleus would remain invisible, just a dark lump of ice and rock drifting silently through space. When a comet approaches a star, however, everything changes. Sunlight penetrates the outer layers, and the ices long preserved in deep freeze begin to vaporize. Jets of gas erupt from cracks and vents, carrying dust with them, expanding into a glowing shroud known as the coma. From that coma, solar wind shapes the iconic tail, a luminous streamer pointing away from the sun. It is this transformation, from silent rock to radiant wanderer, that makes comets the most theatrical actors in the solar system. For most comets we know, water is the main driver of this drama. Near 3 astronomical units from the Sun, water ice begins to sublimate, powering activity that builds the coma. Alongside it, carbon monoxide, carbon dioxide, methane, and other volatiles contribute. But water is the central force. Atlas, however, is rewriting the script. Webb's instruments revealed a startling truth. Carbon dioxide dominates its emissions, outshining water by a ratio of 8:1. This is unprecedented in our catalogue of comets. The implications are profound. It means that Atlas's activity begins earlier, farther from the Sun, because carbon dioxide sublimates at lower temperatures than water. While ordinary comets sleep until they reach warmer zones, Atlas awakens in the cold, venting gas long before water joins the mix. This explains why the comet was active when discovered, and why its coma grew quickly as it approached. It also hints that beneath its surface lies a chemistry moulded in conditions colder than anything in our solar nursery. Outgassing is also a sculptor. The jets that erupt from the nucleus can spin the comet, altering its rotation. They can carve pits, collapse cliffs, and reshape the surface. With Atlas, these processes may be even more chaotic. If carbon dioxide dominates, its plumes may emerge with unusual vigor, producing asymmetries in the coma and pushing the nucleus into irregular tumbles. Polarimetric data already suggest dust clumping in strange ways, perhaps linked to these violent outbursts. The dust itself is shaped by outgassing. Gas jets lift grains of various sizes, from tiny smoke-like particles to larger chunks. The distribution of these grains defines the appearance of the tail, whether broad and diffuse or narrow and streaked. In Atlas, the dust seems to scatter light oddly, a clue that the gas lifting it carries compounds rare in our system. Outgassing here is not just mechanical, it is chemical storytelling, releasing a mixture that tells us where Atlas was born. And outgassing is fleeting. As the comet approaches perihelion, activity peaks, plumes roar, and the coma brightens. But once it passes the Sun and drifts outward, the process fades. The nucleus freezes again, cloaked in silence, carrying whatever ices remain into interstellar night. For Atlas, this will be the last act, its only performance for humanity before it disappears forever. The uniqueness of Atlas's recipe challenges us to expand our models. If water is not the universal driver of cometary activity, then what other chemistries await in the galaxy? Could some systems produce comets dominated by methane, ammonia, or exotic organics? Could others be so depleted in volatiles that their comets barely stir? Atlas shows us that diversity is not theoretical. It is real, glowing in our skies right now. So, when we watch its coma swell, we are not just seeing ice turn to vapor, we are witnessing the exhalation of another world, chemistry preserved for eons and released at last into sunlight. Atlas outgasses not like our comets, but in its own alien rhythm, its plumes whispering of a nursery colder and stranger than our own. October 29th, 2025. The comet swings nearest to the Sun. What new chemistry will awaken in its brief fiery encounter? Perihelion, the closest approach to the Sun, is the moment when a comet reveals its full personality. For months, Atlas has been warming slowly, venting carbon dioxide and scattering strange dust. But as it dives toward the Sun, the intensity of radiation will rise dramatically. Temperatures on its surface will leap by hundreds of degrees, forcing new ices to sublimate, new plumes to roar, and new colors to emerge in its coma. The quiet exhalations of its journey inward will become a storm of activity, as though the comet itself were set ablaze. In most comets, this is when water ice takes over. Too cold to drive activity far from the Sun, water awakens at around 3 astronomical units, and at perihelion it erupts in torrents. Jets shoot out in all directions, expanding the coma and lengthening the tail. For Atlas, though, water has played a minor role so far, overshadowed by its unusual abundance of carbon dioxide. Will perihelion finally unleash hidden reservoirs of water? Or will carbon dioxide remain dominant, marking Atlas as a truly alien wanderer to the very end? The chemistry may evolve in surprising ways. Ices buried deeper in the nucleus, methane, ammonia, even complex organics could ignite under the Sun's heat. These compounds, rare in comets we know, might add unexpected hues or spectral lines to the coma. Already, observers whisper of a faint green shimmer from cyanogen and diatomic carbon. At perihelion, those faint signals could blaze into prominence, painting the comet with exotic colors. But perihelion is not only about chemistry, it is about survival. Comets are fragile things, loosely bound rubble held together by ices. The violence of outgassing, combined with tidal stresses from the Sun's pull, can fracture a nucleus. Many comets have shattered at perihelion, their bright displays ending in disintegration. Atlas could meet the same fate. If its nucleus is small or porous, the fiery encounter may tear it apart, scattering its fragments into space. For astronomers, such a breakup would be bittersweet. The comet lost, but its secrets laid bare in one final burst of data. Around the world, telescopes will be waiting for that moment. Spectrographs will monitor its gases second by second, looking for sudden surges in activity. Cameras will track its brightness, searching for dips and flares that might signal fragmentation. Polarimeters will probe the coma, watching how dust scattering changes as new jets ignite. Every photon counts, because every second of perihelion is unique, never to be repeated. For the comet itself, perihelion is a crossroads. Afterward, its path will carry it outward, back into the deep cold of interstellar space. The ices that survived will refreeze, the plumes will vanish, and the coma will collapse. Atlas will become once more a silent lump, drifting into darkness. Its brief moment of fiery brilliance will pass into memory, both for itself and for us. And yet, perihelion is also a gift. For a few short weeks, Atlas will blaze at its brightest, visible even to modest telescopes, perhaps even to the naked eye under dark skies. It will be a shared experience, a cosmic performance watched not just by scientists but by stargazers around the world. In its glow, we will glimpse not just chemistry, but connection, a reminder that even alien wanderers can unite us in wonder. So as October 29th approaches, the anticipation builds. Will Atlas survive intact, its nucleus scarred but whole? Will it shatter, leaving a trail of glowing fragments? What hidden ices will awaken? What new chemistry will paint its light? Whatever happens, perihelion is the climax of its visit, the moment when its secrets burn brightest, before fading forever into the night. By December, Atlas will dim. By then, Earth will have its last clear view before the visitor vanishes forever. The story of a comet is not only about arrival and climax, it is also about departure. After perihelion, when the Sun's heat has driven its most spectacular outbursts, Atlas will begin its long retreat. At first, the coma may remain brilliant, still fueled by residual warmth. But as the comet moves outward, cooling rapidly, its fountains of gas will weaken. The coma will collapse, the tail will thin, and the bright smudge will shrink into a faint dot. Fade will be gradual, like a lantern guttering as its fuel runs out. By December, Earth will still be close enough to watch, but the comet will already be slipping into the shadows. Amateurs may report only a faint haze, visible through binoculars or long-exposure images. For most of the world, Atlas will vanish from naked eye view if it ever reached it at all. Its performance will be ending, leaving behind silence and data. But fading does not mean meaningless. In fact, the comet's decline may reveal details invisible at its peak. As activity wanes, the coma thins, allowing glimpses closer to the nucleus. Subtle changes in brightness can betray rotation or hint at lingering jets sputtering from deeper layers of ice. Dust tails, once overwhelming, may fragment into fine streaks, their geometry revealing the comet's past eruptions. The timing is poignant. December is a season of endings, of reflection as the year closes. To watch Atlas dim during that month will feel symbolic, another reminder that even great cosmic wonders are fleeting. The comet that once blazed with alien chemistry will recede into invisibility, swallowed by the black. And unlike periodic comets, which return in cycles, Atlas will never be back. Its fade is final, its departure permanent. For astronomers, the last weeks are critical. Data must be gathered before the signal slips below the noise. Coordinated observations will continue as long as possible, telescopes chasing the comet into ever fainter magnitudes. Eventually, even the best instruments will lose it, the dot disappearing into the crowd of background stars. At that point, the comet will belong to memory and to the archives. The fade also underscores the fragility of human connection to these objects. Our encounters with interstellar visitors are always brief. Oumuamua, Borisov. Atlas all appeared suddenly, glowed for a short while, and vanished forever. To follow them is to accept impermanence. We cannot capture them, cannot orbit them, cannot bring them back. We can only watch, learn, and let them go. Yet perhaps that is the lesson. The universe offers its wonders not to be kept, but to be appreciated. Atlas will fade, but the knowledge it leaves will endure. Data about carbon dioxide dominance, about alien dust scattering, about the diversity of comets across the galaxy. Its physical presence will vanish, but its scientific legacy will live on in the papers, models, and memories it inspires. For those who look up, the fade will carry a quiet beauty. To know that the faint smudge drifting into December skies is a piece of another star system is awe enough. Its light may dim, but its meaning will not. It is a reminder that we live in a universe alive with motion, where even the brightest moments are temporary. So by December, when Atlas dims beyond reach, we will bid farewell. The comet will slip into interstellar night, unseen, unheard, carrying with it the frozen story of its birth. And we will be left here on Earth, watching the fade, grateful that, for a brief season, we were able to see it at all. Each interstellar object becomes a ghost in our records. We may never touch them, but their data lingers, enriching our understanding. Oumuamua was the first of these ghosts. A faint streak of light against the stars, it passed too quickly for us to catch, leaving only curves of brightness and speculation in its wake. Borisov followed, a more traditional comet, yet even it faded, leaving behind nothing but images, spectra, and memories. Now Atlas will join them, its alien chemistry preserved not in ice or dust we can hold, but in archives of photons captured by telescopes. One by one, these visitors drift into darkness, transformed into records rather than realities. This is the nature of interstellar discovery. Unlike planets or moons, which can be revisited again and again, these wanderers are one-time encounters. Once they pass, they are gone forever. What remains is not the object itself, but the trace it left in our instruments. A catalogue entry, a set of spectral lines, an orbit plotted against the stars. Each is like the echo of a voice shouted across a canyon. The speaker has moved on, but the sound persists. Astronomers treat these echoes with reverence. Data from Oumuamua is still being analysed years later, its peculiar acceleration inspiring new theories. Borisov's spectra continue to refine our models of cometary diversity. Atlas will be no different. Even as it fades, its chemical fingerprint, dominated by carbon dioxide, will remain a touchstone for decades. Students not yet born will read papers about it, learning what we gleaned from its brief passage. In this way, each ghost enriches us long after its light has gone. A catalogue of ghosts may sound melancholy, but it is also empowering. Ghosts remind us that the universe is alive with activity, that we are not isolated. Every entry in the catalogue is proof that matter flows between the stars, carrying stories from one system to another. They are silent emissaries, unintentional ambassadors of the galaxy's diversity. To study them is to read fragments of countless worlds without ever leaving our own. The ghosts also teach us humility. We cannot hold them, cannot command their return. They remind us of our limitations, of the fleeting nature of discovery. And yet, within those limitations lies a strange beauty. Because each observation is final, it carries a weight we might otherwise overlook. Knowing that we will never see Atlas again makes every photon precious, every measurement profound. Its ghost will not be just another entry. It will be a singular chapter in the story of our encounter with the galaxy. In time, the catalogue will grow. More ghosts will arrive, discovered by ever-watchful surveys. Some will be faint specks, their data sparse. Others will blaze, rich with chemistry and dust. Together, they will form a mosaic of diversity, a ghostly census of alien systems. And while each individual visitor may be gone, the collective will shape our understanding of planetary formation, chemistry, and the abundance of life-building materials across the Milky Way. The ghosts may also serve another role: preparation. By studying them, we learn what to expect when we finally send probes to intercept one. The catalogue becomes a training ground, teaching us how to recognize anomalies, how to design instruments, how to interpret alien chemistries. Ghosts may be unreachable, but they guide us toward the day when we will catch one alive. So yes, Oumuamua, Borisov, Atlas, they are ghosts now, drifting beyond sight. But in their wake, they leave us richer, wiser, more connected to the universe. A catalogue of ghosts is not a record of loss. It is a testament to discovery, to the fleeting but profound moments when another star system brushed against ours and left behind its silent trace. One object is a curiosity. 3 begin a pattern. Soon, we may build a census of interstellar debris, shaping galactic science. Oumuamua, in 2017, was a shock, a singular anomaly that raised more questions than answers. Borisov in 2019 confirmed what many suspected: that our galaxy is full of wanderers, fragments flung from other systems. Now, Atlas adds a third point on the graph, not only reinforcing the case but also expanding it with chemistry stranger than either of its predecessors. 3 objects do not yet make a complete story, but they mark the beginning of one. The vision is bold: a galactic census of interstellar debris. Just as naturalists once catalogued species to map the biodiversity of Earth, astronomers are now beginning to chart the diversity of alien fragments that pass through our solar system. Each interstellar object is a sample, drawn at random from the galaxy's great experiment in planetary formation. Together, they can reveal how common certain chemistries are, how planetary systems differ, and perhaps even where life-building materials are most abundant. To build this census, we need numbers. How often do interstellar objects pass through? Are most cometary, like Borisov and Atlas, or rocky and enigmatic, like Oumuamua? What size distribution do they follow? Are tiny fragments far more common than large comets? Do they come from systems like ours, or from exotic nurseries orbiting faint red dwarfs? A census transforms these questions from speculation into statistics, turning stories of individual visitors into a coherent galactic narrative. The tools for this work are already coming online. The Vera C. Rubin Observatory will scan the sky with unmatched sensitivity, detecting faint, fast-moving objects years before perihelion. Combined with existing surveys like Pan-STARRS and Atlas, this will create a near-continuous watchtower for interstellar arrivals. With time, the catalogue may grow from 3 to dozens, then hundreds. Each new entry will refine our understanding, shrinking the uncertainty around the true population of wanderers. And with numbers comes comparison. Imagine a database of interstellar spectra, each barcode of chemistry filed alongside orbital details. Patterns will emerge. Some objects dominated by water, others by carbon dioxide, some perhaps rich in exotic organics. Dust polarization curves will reveal how alien grains differ from our own. Rotational states, sizes, and tail morphologies will hint at the dynamics of their birth systems. The census will become more than a list, it will be a galactic map, showing how star systems scatter their fragments into space. The implications reach beyond curiosity. By analyzing which chemistries are most common, we learn about the environments that dominate the galaxy. If water-rich comets prove plentiful, then icy outer belts like ours may be typical. If carbon dioxide dominates, as in Atlas, then perhaps colder or more exotic systems are widespread. Such knowledge feeds into astrobiology, shaping our sense of where habitable planets may form and how often life's ingredients travel between stars. A census also prepares us for opportunity. With enough detections, we can predict the frequency of close passages, those rare times when a large interstellar comet sweeps near Earth, bright enough for naked eye viewing or accessible enough for a rapid response mission. Knowing the odds allows us to design spacecraft, build interceptors, and be ready. What now feels like chance could soon feel inevitable. So while Oumuamua, Borisov, and Atlas are ghosts fading into the void, they are also heralds of a new science. No longer will interstellar visitors be singular anomalies. They will be data points in a census, threads in a larger tapestry of galactic science. With patience, vigilance, and technology, humanity is building not just a catalogue of wanderers, but a record of how the Milky Way itself breathes, scatters, and evolves. The census has only just begun. And Atlas, in its brief bright passage, is one of its first entries, a line in a ledger that may one day describe the galaxy in full. Atlas shows us that not all comets are alike. Star systems build different recipes, sculpting alien chemistry into icy messengers. For centuries, comets were thought of as a single kind of object. Dirty snowballs of ice and rock, their variations merely details of orbit and brightness. But the arrival of interstellar wanderers has rewritten that picture. Oumuamua defied our expectations entirely, with no coma at all and a shape unlike any known body. Borisov reassured us, behaving almost exactly like a solar system comet. Now Atlas adds a third chapter, revealing that even among comets, there is no universal recipe. Its carbon dioxide-rich outgassing shows that comets are not copies of one another, but unique expressions of the environments in which they form. The chemistry of a comet is a direct imprint of its nursery. In our solar system, most comets formed in the outer regions, where water ice is abundant and stable. That is why water dominates their activity. But Atlas tells us that in another system, conditions were colder or different enough for carbon dioxide to become the primary volatile. Perhaps the star was dimmer, or its disk extended farther into deep freeze. Perhaps radiation or stellar winds stripped water early, leaving carbon-rich compounds behind. Whatever the case, Atlas is a living demonstration that the galaxy produces many versions of comet, each tuned to its environment. This diversity is not surprising when we consider the stars themselves. Some systems orbit hot, bright suns. Others circle dim red dwarfs. Still others are born in clusters, their disks bombarded by nearby stars. One forged in a radiation-heavy region might carry complex organics or nitriles. Another could be almost devoid of volatiles, a rocky shard masquerading as a comet until sunlight reveals its barrenness. Atlas is one example among what must be countless variations. Dust grains add to the diversity. The scattering patterns of Atlas's coma suggest alien textures, perhaps clumped or coated in compounds rare in our solar system. This points to differences not only in chemistry, but in physical processes. How grains stuck together, how collisions shaped them, how radiation altered them over time, just as snowflakes on Earth never repeat. No two comets in the galaxy are likely the same. Each is a frozen fingerprint of its star system, a unique archive of its conditions. The lesson is profound. For too long, astronomy assumed our solar system was typical, that water-driven comets were the standard template. Now we see that was an Earth-centered assumption. Atlas reminds us that diversity is the rule, not the exception. The universe is a vast laboratory, running countless experiments in planetary formation. Some results look like Borisov, some like Oumuamua, some like Atlas. Each is valid, each is real, and each expands our sense of what is possible. This diversity also feeds into the question of life. If comets are delivery systems for water and organics, then their chemistry shapes the likelihood of habitability. A system rich in water comets may seed its planets with oceans. A system dominated by carbon dioxide comets may deliver different building blocks. Diversity across comets mirrors diversity across planets, reminding us that life itself may arise in countless forms, depending on the ingredients scattered by these icy messengers. So when we watch Atlas glow, we are not just seeing one comet. We are seeing evidence that the galaxy is filled with variety, that the recipes of creation are endless, and that every star writes its own version of a cometary story. Atlas is not strange because it is rare. It is strange because it is new to us, a representative of a diversity we are only beginning to glimpse. The cosmos is not uniform. It is rich, varied, and endlessly inventive. And comets like Atlas are the proof, shimmering in our skies as emissaries of that truth. JWST was designed to see galaxies billions of light years away, yet here it is, decoding the chemistry of a comet in our backyard. When the James Webb Space Telescope launched in December 2021, its mission was framed in grand cosmic terms. It would peer into the early universe, study the first galaxies, and unravel the mysteries of star formation. Its infrared eyes, shielded by a sunshade the size of a tennis court, were built to capture the faintest whispers of ancient light. Yet, as often happens in science, a tool built for one purpose reveals wonders in another. In the case of Atlas, Webb's instruments turned their focus from the edge of the observable universe to a small, glowing visitor drifting through our solar system, and the results were astonishing. Webb's power lies in its ability to break light into exquisite detail. Its spectrographs can identify molecules at levels of precision unmatched by any other telescope. When scientists pointed Webb at Atlas, they expected to confirm the usual suspects: water vapor dominating, with supporting lines from carbon dioxide, carbon monoxide, and perhaps a few organics. What they found instead rewrote the script. Carbon dioxide overwhelmed the spectrum, its lines 8 times stronger than water. For the first time, humanity had proof that a comet could be built on a completely different recipe than the ones we know. This discovery was more than chemistry, it was proof of concept. Webb showed that it could do planetary science as well as cosmology. It could not only look at galaxies 13 billion years old, but also decode the volatiles of a comet just a few astronomical units away. In doing so, it bridged the scales of the cosmos, reminding us that the same physics governs both the most distant galaxies and the icy heart of a small traveller in our own skies. The data also carried nuance. Webb's spectrographs revealed faint traces of other compounds, perhaps carbon monoxide, perhaps nitrogen-bearing molecules, adding complexity to the picture. Combined with observations of dust scattering and polarization, the results painted Atlas as an object both comet-like and alien, similar in behavior yet distinct in substance. Without Webb, this subtle chemistry would have been invisible. Ground-based telescopes could only hint at it, blurred by Earth's atmosphere. Webb proved that space-based infrared observation is essential for decoding interstellar visitors. Equally important was timing. Atlas was discovered early enough for Webb to schedule observations before perihelion, when the comet was still inbound and growing brighter. Oumuamua had slipped away too fast. Borisov was studied but with less detail. Atlas became the first interstellar comet fully examined by Webb at its peak, establishing a new benchmark for what is possible. Future discoveries will follow this model, with Webb and its successors poised to turn interstellar anomalies into data-rich case studies. Beyond Atlas itself, Webb's achievement proved a broader truth. With tools like Webb, we can extract the fingerprints of alien chemistry with precision. We can begin to compare objects systematically, to see patterns, to move from anecdotes to science. Atlas is not just a comet, it is a proof that our instruments are ready, that humanity has the capability to study visitors from other stars with the same rigor once reserved for planets and galaxies. And so, Webb's gaze on Atlas is more than a technical triumph, it is symbolic. It shows that even the grandest instruments, built to probe the edge of time itself, have roles to play in the immediacy of our solar system. The universe is one continuum, from the smallest comet to the largest galaxy. Webb has proven that, and Atlas is the messenger carrying that lesson home. Every moment counts. Once Atlas swings away, we cannot call it back. Our instruments must learn quickly, or lose the chance forever. Interstellar visitors are gifts wrapped in impermanence. Unlike the planets or moons of our solar system, which wait patiently for us to study them year after year, a comet like Atlas is fleeting. It arrives without warning, shines for a season, and then departs forever. There will be no second orbit, no chance to return, no promise of a repeat. Time, therefore, is the rarest commodity. Every second of observation matters, because once the moment is gone, it is gone for eternity. The story of Oumuamua is a cautionary tale. Discovered only after its perihelion, it had already passed its brightest point. Astronomers scrambled to capture data, but the window closed too quickly. Most of what we know is speculation, built on faint light curves rather than rich spectra. Borisov, by contrast, was found inbound, giving scientists months to prepare. Even so, its rapid motion and faintness limited what could be gathered. Atlas, at last, arrived early enough to allow a full campaign, but even with Webb and Earth-based telescopes at the ready, the clock ticks relentlessly. Time shapes not only what we see, but how we interpret it. A comet's activity evolves daily as it approaches the Sun. Early spectra tell one story, dominated by volatiles that sublimate at low temperatures. Weeks later, new molecules join as the nucleus warms, while dust grains change their scattering as jets erupt. To miss even a few nights is to lose entire chapters of the comet's narrative. That is why astronomers schedule overlapping observations across the globe, ensuring that the comet is never out of view. The fragility of time demands vigilance. The urgency is not just observational, it is existential. Atlas is moving too fast for any spacecraft to catch. We will never fly alongside it, never sample its nucleus, never send probes to orbit or land. Our only contact is through light, and light must be gathered now, before the visitor fades. If our instruments are not ready, the story will slip through our fingers, leaving behind only regret. Time lost cannot be reclaimed. And yet, this fragility carries a strange beauty. Knowing that the opportunity is brief makes the act of observation more meaningful. A photon captured by Webb's detectors is not just a measurement, it is a relic, a piece of information carried across light years, arriving in our instruments during the only moment it ever will. Each data point is precious, a thread pulled from the fabric of the galaxy and preserved in human memory. Astronomy has always been about patience, waiting for orbits, waiting for alignments, waiting for technology to catch up. But interstellar visitors invert that rhythm. They demand urgency, action, and readiness. Atlas reminds us that the cosmos does not wait for us to be prepared. It will pass whether or not we are watching. The fragility of time is both a challenge and a call to action. To build better surveys, to maintain flexible instruments, to respond quickly when the next visitor arrives. One day, perhaps, humanity will be ready with Interceptor's spacecraft standing by, capable of rapid launch to meet these wanderers in person. Until then, our only defense against the loss of time is vigilance. Telescopes must sweep the skies, software must flag anomalies, scientists must act without hesitation. Because in the end, we cannot call Atlas back, we can only catch it in this brief moment and then watch as it vanishes forever into the night. Time is fragile, but within that fragility lies the heart of discovery. To measure the fleeting is to honour it, and to honour it is to ensure that even as Atlas disappears, its lessons remain. Some call it harmless. Others cry doom. Media shapes the comet's story differently, even as the science remains steady. Whenever a comet appears, it seems to take on two lives, the measured reality of science and the emotional narrative of the public. For Atlas, astronomers see an interstellar visitor rare, intriguing, but not dangerous. Its hyperbolic trajectory ensures it will never strike Earth. Its chemistry is unusual, but entirely natural. Yet in headlines and social feeds, the story bends. Some outlets emphasize its beauty, portraying it as a celestial gift. Others paint it as a harbinger, reviving old fears of comets as omens of disaster. This divide is not new. History is filled with moments when comets inspired awe and dread in equal measure. The Great Comet of 1680 was described as both a divine warning and a miracle of creation. Halley's Comet in 1910 brought both celebration and panic. Some feared its cyanogen gases would poison the Earth. Today, the fears may take more modern forms, reframed through the language of doomsday predictions or conspiracy theories. In every age, comets have carried stories beyond their science. Atlas is no exception. Its interstellar origin fuels fascination. To some, that makes it an alien messenger, a sign of mysteries beyond comprehension. To others, it sparks darker imaginations. The idea of hidden threats, government cover-ups, or catastrophic impacts. Despite astronomers' calm reassurances, speculation thrives in the spaces where knowledge is incomplete. A faint green glow, for example, is explained as excited diatomic carbon, but in rumour it becomes a signal, a weapon, or proof of alien technology. Meanwhile, science moves forward quietly, steady in its methods. Observatories log spectra, measure dust scattering, refine orbits. Papers describe carbon dioxide ratios and coma polarization, not prophecies or perils. Yet these findings rarely reach the public with the same impact as dramatic headlines. It is easier to spread fear than chemistry. It is easier to sell mystery than data. The uneven gaze persists because wonder and worry both have stronger hooks than quiet fact. And yet, the fascination has value. Public attention, even when uneven, can support funding, inspire students, and remind society of the beauty of science. If Atlas is painted as an omen, it still captures imaginations. If described as an alien visitor, it still sparks curiosity. Astronomers must then step in to redirect that curiosity, to show that the true story, the chemistry, the physics, the galactic context is just as compelling as the myths. The comet itself is indifferent. It neither threatens nor comforts, neither communicates nor conceals. It simply follows its path, venting gases into sunlight. The stories layered onto it are human creations, reflections of our hopes, fears, and need for meaning. In that sense, the uneven gaze reveals as much about us as it does about Atlas. We see in it what we want to see. A mirror for our culture as much as a window to the stars. The task of science communicators, then, is to bridge the divide, to take the raw awe the public feels and guide it toward understanding, to show that the strangeness of carbon dioxide dominance, the beauty of green fluorescence, the poignancy of a one-way journey are stories powerful enough without embellishment. The comet is wondrous, not because it is dangerous, but because it is real. So, as Atlas drifts across our skies, the narratives will diverge. Some will call it harmless, some will cry doom, but in the steady light of science, it is neither. It is simply extraordinary, a visitor from another star, luminous for a moment, then gone. The uneven gaze will pass, but the knowledge will remain. Astronomers describe its luminous veil. To the naked eye, faint. To the telescope, breathtaking, an ice-borne ribbon across the void. The tail of a comet is one of the most iconic sights in astronomy, a reminder that even small, fragile bodies can weave vast tapestries of light. For Atlas, the tail is more than spectacle. It is a story written in dust and gas, unfolding across millions of kilometers. To look at it is to read the comet's diary, a record of its chemistry, its interaction with the sun, and its alien origins. To the unaided eye, Atlas's tail may appear only as a faint smear, if at all an ephemeral glow against the background stars. But through telescopes, it stretches magnificently, a filamentary arc carved by sunlight and solar wind. Its dust component gleams softly, reflecting starlight, while the ion tail shines with ghostly blue hues as charged gases fluoresce under the sun's ultraviolet rays. Each component moves differently. The dust tail curving gently along the comet's orbit, the ion tail streaming straight outward, aligned with the solar wind. Together, they form a double ribbon, delicate yet immense. Atlas's chemistry gives its tail a special character. Dominated by carbon dioxide rather than water, its emissions shift the balance of what we see. Molecules like CO2 and CO can fluoresce in unique wavelengths, painting subtle differences into the ion tail. Meanwhile, dust grains lifted by these gases scatter light in unusual patterns, giving astronomers clues about their size, texture, and composition. The shimmering veil is not just beautiful, it is a laboratory in motion, revealing the comet's secrets at cosmic scale. The tail is also alive. Each night it changes, reshaped by the interplay of solar forces. A burst of outgassing can send jets of dust spiraling outward, creating striations. A surge of solar wind can twist the ion tail, snapping it into kinks or detaching entire sections. Observers have reported disconnection events in comets before moments when the ion tail breaks away under a storm of particles from the sun, only to regrow again. Atlas may show the same, a fragile ribbon constantly renewed, never the same twice. From Earth, long exposure photographs capture its majesty, turning faint wisps into grand arcs. To the eye, these images look unreal, too vast, too delicate to belong to reality. Yet they are real streams of dust and gas stretching millions of kilometers, drawn from a nucleus no wider than a city. The contrast is staggering. A tiny icy core, cloaked in a tail so immense it could engulf worlds. Culturally, the tail carries deep resonance. Ancient civilizations saw comets as swords in the sky, their tails blazing like omens. Today, we see them as natural, but the sense of wonder persists. The sight of Atlas's ribbon across the void reminds us of the universe's ability to create beauty, from violence, sublimation, erosion, radiation processes destructive at the nucleus but magnificent at a distance. For astronomers, the tail is more than art. By studying its brightness and shape, they can measure the amount of dust, the rate of outgassing, and the nature of the grains. Spectroscopy of the ion tail reveals its molecular composition, turning its glow into data. Polarization studies decode how light scatters off particles, offering hints about textures alien to our solar system. Every shimmer is a clue, every filament a fact. So while the naked eye may see little, the telescope reveals a masterpiece. A ribbon of alien chemistry painted across the dark canvas of space. Atlas's tail is not just a byproduct. It is the visible expression of its essence, the evidence of its activity, the art of its physics. And when it fades, the memory will linger. The beauty of the tail is not only in its form, but in its ephemerality, a glowing reminder that some of the most breathtaking wonders of the cosmos are the ones that will never appear again. Interstellar debris drifts like discarded letters, carrying the chemistry of forgotten nurseries, delivered to our solar system's doorstep. Each interstellar object that arrives is a fragment of a world we will never see, a sample cast off during the restless youth of another star system. Giant planets fling icy bodies outward like pebbles in a sling. Stellar encounters jostle them loose, scattering them into the galactic sea. For billions of years, these fragments wander aimlessly, like undelivered letters, until one drifts near our sun and briefly becomes visible. Atlas is such a letter, a piece of cosmic junk mail, addressed to no one, but delivered nonetheless. Unlike carefully written messages, these fragments do not intend to communicate. They are accidents of gravity. Yet, by chance, they carry chemistry, structure, and stories of their origins. In Atlas, we see a system where carbon dioxide ruled over water, where dust grains took on alien textures, where the familiar recipes of our solar system were rewritten. The comet is not a message in words, but in molecules, a language we are only beginning to decipher. The metaphor of junk mail is fitting because of its randomness. Most of the time, these interstellar letters pass by unseen, too faint or too far for us to notice. Only recently, with powerful surveys scanning the skies nightly, have we begun to catch them. Oumuamua slipped past unnoticed until too late. Borisov lingered just long enough for us to glimpse. Atlas, brighter and found early, gives us a chance to read more carefully. But for every one we detect, countless others likely pass silently in the dark. And just like discarded letters, the debris can be surprising. Some may be small scraps, barely meters across, unnoticed unless they streak into our atmosphere. Others may be massive, icy worlds the size of cities, glowing spectacularly as they pass. Each is unique, shaped by the conditions of its birth. One carries mostly water, another mostly carbon dioxide. Perhaps another still, waiting to be found, will carry complex organics or unusual metals, fragments of a disk unlike anything we know. For science, junk mail is anything but trivial. Each fragment adds to the mosaic of galactic diversity, helping us understand how planets form and evolve. By comparing one letter to another, we begin to see the patterns, which chemistries are common, which are rare, which are tied to certain types of stars. Over time, the pile of discarded mail becomes a census, not of intentional messages, but of the galaxy's ordinary workings, its waste products, its cast-offs, its silent testimonies. Yet there is also poetry in this randomness. To think that our solar system is not isolated, but constantly intersected by fragments of others, is humbling. We are not alone in the sense of being connected not by communication, but by debris. Every interstellar visitor is proof that the galaxy is dynamic, that material flows across its expanse, that what forms in one nursery does not stay there forever. It drifts, it wanders, and sometimes it comes to us. Atlas, then, is not a letter meant for us, but one we are lucky enough to intercept. Its tail is the envelope torn open by sunlight. Its fleeting presence is a reminder that the universe is full of forgotten scraps, waiting to be discovered. So while we may call it junk mail, it is treasure to us, an uninvited, accidental delivery that enriches our understanding of the cosmos. And though Atlas will leave, fading into the void, the letter it brought has already been read, and its story will remain with us long after it is gone. These visitors are small, yet they reveal something vast. The endless variety of planetary systems scattered across the Milky Way. At first glance, comets like Atlas are humble things. A nucleus perhaps only a kilometre across, fragile enough to shatter under the stress of sunlight. Against the scale of the solar system, it is nothing. Against the sweep of the galaxy, it is less than a grain of sand. And yet, in that tiny body lies a story as wide as the Milky Way itself. A story of how worlds are built, how systems evolve, and how matter flows between stars. Atlas is small, but the perspective it brings is enormous. Every interstellar object is proof that planetary systems do not remain sealed. The Milky Way is not a collection of isolated bubbles, but a web of exchange. Atlas, Oumuamua, Borisov, each is a reminder that the chemistry of the galaxy is shared, shuffled, and redistributed across unimaginable distances. The scale is not local. It is galactic. When we detect a comet's coma, we are not simply seeing sublimation. We are seeing the echoes of conditions billions of years old, preserved in ice. Atlas's carbon dioxide dominance tells us that its parent system was colder than ours, or that its chemistry followed a different path. Multiply that by billions of stars, and we glimpse the vast spectrum of possibilities across the galaxy. Some systems might produce water-rich comets, others might favour methane or ammonia. Still others may eject rocky bodies with little ice at all. Each small fragment points towards something vast, the diversity of planetary nurseries across the Milky Way. The reminder of scale comes also in time. Atlas's journey likely began hundreds of millions, perhaps billions, of years ago. It has wandered interstellar space longer than humanity has existed, longer than Earth's continents have rested where they are now. To see it now is to witness an object that has outlasted civilizations, continents, even species. Its brief passage through our sky is a footnote in its ancient odyssey. What to us is fleeting, a few months of visibility is, to the comet, merely another moment in a journey that spans galactic ages. There is humility in this scale. We live on a planet rich with life, orbiting a star that feels central to us. But Atlas reminds us that our star is just one of hundreds of billions, our system just one experiment among countless others. The comet is a messenger of perspective, whispering that the universe is larger, older, and more varied than we can easily imagine. It is a humbling reminder that the Milky Way does not revolve around us, and yet we are privileged to glimpse its workings. And yet, the scale is not only humbling, it is exhilarating. To know that our instruments can capture the chemistry of an object from another star, to know that our telescopes can decode its light, is to feel connected to something vast. It is proof that even from our small planet, we can reach into the galaxy and pull out knowledge, bridging scales from the microscopic to the cosmic. The comet may be small, but its significance is vast, because it expands the scale of what we know. So Atlas is not just an icy fragment. It is a reminder of scale in size, in time, in diversity. It shows us that the galaxy is not static, but alive with exchange, a grand cosmic marketplace of matter. And it reminds us that even the smallest visitor can carry the weight of the Milky Way within its fragile, glowing form. Each interstellar comet carries clues about the star system that birthed it, snapshots of the chaos of planetary formation. When we look at Atlas, we are not simply observing a comet. We are peering into the earliest chapters of another star system's history. Comets are leftovers, the icy remnants of worlds that almost formed but never did. In our solar system, they linger in the Kuiper Belt and Oort cloud, time capsules of the conditions present when the planets emerged. Atlas, by contrast, is an exile, a fragment ejected from its birthplace, carrying the chemistry and structure of its nursery across interstellar space. In its gases and dust, we can read echoes of planetary birth written long before Earth itself existed. Planetary formation is a violent, inefficient process. Protoplanetary disks, vast swirls of gas and dust around young stars, spawn planets by accreting material together. But not all matter joins the party. Much of it is scattered outward by gravitational encounters with giant planets. Others are launched outward entirely, expelled from the system at escape velocity. Atlas is almost certainly one such exile, flung into the void by the restless dance of a giant world billions of years ago. Its chemistry reveals details of that nursery. The dominance of carbon dioxide over water suggests that it formed in a region colder than the zones where our comets typically accreted. Perhaps it condensed in the outermost reaches of its system, where sunlight was weak and CO2 ice stable. Perhaps its star was dimmer than our Sun, a red dwarf whose habitable zone lay close in, leaving its outer regions perpetually frozen. Whatever the specifics, Atlas preserves a frozen record of those conditions, unchanged, during its lonely drift through the galaxy. The dust it carries tells an equally vivid story. The scattering patterns hint at textures not seen in our comets, maybe grains coated with exotic organics, maybe clusters that clumped under conditions unfamiliar to us. Dust grains are the seeds of planets, the first building blocks that eventually snowball into worlds. In Atlas's dust, we glimpse not just a comet's history, but the materials that once sought to become planets and perhaps even homes for life. Even its trajectory tells us something. For Atlas to reach us, it had to survive the hazards of its own system. Collisions, radiation, gravitational chaos. It had to endure millions or billions of years adrift in interstellar space, bombarded by cosmic rays yet still carrying intact ices. That endurance is itself a clue to the robustness of planet-forming material across the galaxy. These fragments are not fragile sparks that vanish easily. They are tough enough to wander for ages, still bearing witness when they pass by another star. When we study Atlas, then, we are not just learning about one comet. We are reconstructing the processes of planet formation writ large. By comparing Atlas to Borisov and to our own comets, we see variations on the theme. How disks can produce water-rich bodies, TO2, rich bodies, rocky fragments, or strange hybrids. The diversity of comets is the diversity of planetary nurseries. Each interstellar visitor is a missing page from the story of how the galaxy builds its worlds. And while we may never know Atlas's home star, we know that such stars are everywhere. Every point of light in the night sky may be surrounded by its own belts of icy debris, scattering comets into the void. Some of those comets drift our way, carrying whispers of their origins. Each is an echo, brief, faint, but invaluable. So, as Atlas brightens and then fades, remember, we are watching not just a comet, but the aftermath of planetary birth, preserved across the ages. It is a frozen snapshot of another system's beginning, carried here like driftwood from a distant shore. In studying it, we come closer to understanding how worlds like ours are born, not just here, but everywhere among the stars. Atlas forces us to ask, is our solar system typical, or is it just one story among countless strange variations? For much of history, humanity assumed that our solar system was the model for the universe. The sun, the planets, the icy comets, all seemed like the natural template. When astronomers first discovered exoplanets in the 1990 seconds, that assumption began to crumble. Hot Jupiters, super-Earths, planets orbiting binary stars all revealed that our system might be less normal and more particular. Now, interstellar comets like Atlas deepen the question. If Atlas is built on a recipe dominated by carbon dioxide rather than water, then our own water-rich comets may not be the universal standard we thought they were. Atlas's chemistry challenges the idea of normalcy. In our backyard, comets are dominated by water. Around another star, CO2 may be king. That alone hints at profound differences in how planetary systems form and evolve. Was Atlas born in a colder disk than ours, around a dimmer star? Was water scarce in its nursery, or was carbon dioxide simply more available? Each possibility reframes our sense of what planetary formation looks like elsewhere. Our solar system is not the baseline, it is one experiment among billions. This realization echoes across astronomy. When astronomers first found planetary systems, many were shocked to see gas giants hugging their stars, something absent in ours. Over time, the shock faded, replaced by the understanding that diversity, not uniformity, defines the galaxy. Atlas carries that lesson into the realm of comets. What we assumed was normal water-rich comets orbiting in long ellipses may be just one variant, no more universal than a hot Jupiter or a super-Earth. The question of normal reaches deeper, into life itself. If comets deliver the raw ingredients for habitability, then their chemistry shapes what kinds of worlds are seeded. A system dominated by water comets may give rise to oceans like Earth's. A system dominated by carbon dioxide comets may evolve differently, perhaps enriching atmospheres with greenhouse gases or altering planetary climates in unpredictable ways. Atlas forces us to consider that even life's potential may not follow a single template. There is humility in this perspective. For centuries, we viewed our system as the measure of all things. Now, each interstellar visitor peels back that illusion. Oumuamua, Borisov, Atlas, all whisper the same truth. We are not the norm. We are one story among many, shaped by chance and chemistry. Somewhere else, a system rich in methane might see comets blazing with blue-green flames. Somewhere else, comets might barely outgas at all, their ice is depleted, their skies dark. Every variation is a new possibility, a reminder that normality is an illusion in a universe this vast. And yet, there is comfort here too. Diversity does not diminish us, it connects us. Atlas may not look like our comets, but it proves that comets exist everywhere. Our solar system is not alone in producing icy messengers, it is part of a galactic chorus, each voice singing in its own key. To ask whether we are normal may miss the point. The point is that we are part of something larger, a shared process of creation playing out across the stars. So, is our solar system typical? Perhaps not, but typicality may not matter. What matters is that we are one thread in a vast tapestry, unique in detail but universal in origin. Atlas reminds us that there are countless variations of planetary systems, each with its own comets, its own chemistry, its own potential for life. Our story is just one among many, and that, in itself, is extraordinary. Atlas is not the end. With our eyes now sharper than ever, the next interstellar object may already be inbound. The discovery of Oumuamua in 2017 was an accident, a chance glimpse of an object already leaving. Borisov, 2 years later, was found earlier, granting astronomers more time. Atlas, discovered inbound, has offered the richest window yet. With each visitor, our ability to detect improves, our readiness sharpens. The story is not closing, it is just beginning. Somewhere in the dark beyond Neptune, another wanderer may already be streaking toward us, unseen but inevitable. Surveys like Pan-STARRS, Atlas, and soon the Vera C. Rubin Observatory ensure that fewer of these visitors will slip by unnoticed. Rubin, in particular, will scan the entire sky every few nights, detecting faint, fast-moving objects years before they grow bright. That means the next interstellar comet could be spotted long before perihelion, giving scientists unprecedented preparation. Instead of scrambling for telescope time, astronomers will be ready, instruments tuned, missions perhaps even launched. The prospect excites scientists not because each visitor is the same, but because each is different. Oumuamua carried no coma, its acceleration still puzzling. Borisov behaved like a textbook comet, water-driven and familiar. Atlas split the difference, with chemistry dominated by carbon dioxide and dust scattering in strange ways. The next object may bring an entirely new twist, perhaps an ice-rich body glowing bright green, or a rocky fragment barely distinguishable from an asteroid. Each new arrival adds another data point, another hint at the galaxy's diversity. But preparation is not only about telescopes. Concepts like Project Lyra and other interceptor missions imagine spacecraft designed to launch quickly when the next object is found. Instead of chasing too late, as with Oumuamua, we could meet a visitor up close, sampling its dust, imaging its nucleus, and decoding its chemistry in situ. If Atlas has taught us anything, it is that every visitor carries unique and irreplaceable knowledge. To let the next one pass unstudied would be a loss too great. The anticipation carries a sense of inevitability. Estimates suggest that at any given time, thousands of interstellar fragments pass through the solar system, most too small or faint to notice. If our instruments are sensitive enough, we will not see one every decade, but perhaps every year, or every few months. The universe is busy, and we are only now learning to watch. The next discovery could be tomorrow, or it could already be hidden in survey data, waiting to be recognized. There is poetry in this waiting. To know that another emissary from a distant star is on its way, carrying chemistry we have never seen, is to live in a state of perpetual expectancy. Somewhere in the darkness, a tiny icy body drifts closer, unaware of the attention it will soon command. For now it is anonymous, one of countless fragments between the stars. Soon it will have a name, an orbit, a story. Soon it will join the growing family of interstellar visitors that reshape our understanding of the galaxy. So Atlas is not the end. It is part of a chain, a chapter in an unfolding book. Each comet, each fragment, each glowing trail across the night is a reminder that the galaxy is alive with motion and variety. The next visitor awaits, and when it comes, we will be watching with sharper eyes, better tools, and deeper questions. What chemistry will it reveal? What story will it tell? And how will it expand the fragile but growing map of interstellar wanderers we are building? We are not yet travelling to other stars, but the stars, in a way, are sending pieces of themselves to us, and we are learning to listen. For centuries, the dream of interstellar exploration has felt impossibly distant. The stars are too far, the distance is too vast. Even our fastest spacecraft would take tens of thousands of years to reach the nearest system. But in their own quiet way, the stars have been reaching out to us all along. Interstellar comets like Oumuamua, Borisov, and now Atlas are emissaries, pieces of other systems drifting into ours, carrying chemistry and history across the gulf. We are not yet travellers, but we are recipients. The cosmos is speaking. Our task is to learn its language. Listening begins with light. Every photon from Atlas is a messenger, carrying the imprint of molecules and dust grains. Spectrographs break that light apart, revealing barcodes of chemistry that tell us whether carbon dioxide, water, or something stranger dominates. Polarimetry reveals how dust is shaped and clumped. Imaging shows the behavior of the coma and tail, shifting night by night. But listening is also about patience. These objects do not stay long. Each is visible for only a few months before fading into the dark. The data must be gathered carefully, compared across instruments, and interpreted with humility. Oumuamua still resists easy explanation. Borisov reassured us with familiarity. Atlas startles us with its carbon dioxide dominance. Each voice is distinct, each accent shaped by a different nursery. The chorus is still small, but it grows. There is a profound intimacy in this act. These comets are not distant galaxies, billions of light years away. They are nearby, close enough that their dust and gases brush against sunlight and reach our telescopes. They are tangible in a way few cosmic objects are. They remind us that the galaxy is not only out there, unreachable, but also here, touching us directly with its fragments. The universe is not silent. It is whispering through debris, and we are finally learning to listen closely. And what we hear changes us. From Atlas, we learn that water is not universal, that carbon dioxide can dominate. From Oumuamua, we learn that some bodies carry no coma at all, their shapes strange and unexplained. From Borisov, we learn that not all interstellar wanderers are exotic, some are comfortingly familiar. These lessons remind us that the galaxy is vast in possibility, that no single system is the standard. Listening shows us that normal is an illusion, and diversity is the truth. The act of listening also prepares us for the future. Each fragment teaches us what to expect, how to design better instruments, how to prepare missions that might intercept the next. To listen well now is to build the capacity to engage more deeply later, perhaps even to one day send probes to the stars themselves. Listening is the first step in every journey, the foundation of every response. Perhaps the most beautiful truth is this: the universe does not require our permission to speak. It sends its fragments unbidden, scattering them across the void. Our role is simply to notice, to pay attention, to treat each visitor as the gifted island. We are not travelling yet, but already we are in conversation. Atlas is only the latest voice in that cosmic exchange, one we were fortunate enough to hear. Each will carry its own chemistry, its own whisper, its own story. And as long as we listen, the universe will keep speaking, one fragment at a time. And so, the story of Atlas begins to fade, much like the comet itself will in the months to come. We followed its path from discovery to departure, traced its strange chemistry, and pondered the mysteries it carries from a star system we will never see. We've asked whether our solar system is normal, whether life's ingredients may be scattered by these icy travellers, and whether one day we might be ready to meet such a visitor up close. In the end, Atlas is more than a comet. It is a reminder that the universe is vast and varied, that we are part of something larger than ourselves, that even the smallest fragment of ice and dust can illuminate truths about planetary birth, galactic diversity, and the connections that bind the cosmos together. As you close your eyes tonight, let yourself drift with Atlas. Imagine its long journey through the dark, carrying frozen chemistry across billions of years, until at last it passed close enough for us to see. Imagine the silence of that journey, the patience of time, the stillness of the void. And then imagine the brief burst of brilliance, when sunlight awoke it, and its story was revealed. We are fortunate to live in an age where we can listen to such whispers from the stars, fortunate to witness, to wonder, and to learn. And for that, we can be grateful for the chance to be part of this universe even for a short while. Rest now, knowing that the cosmos is still unfolding its stories, and that tomorrow will bring new wonders. May your dreams tonight carry you among the stars, where comets like Atlas continue their eternal voyage through the quiet sea of the galaxy.